prediction.
No, you're not. But yeah, but on the other hand, it does look like it's happening already, right? You are giving a talk in Montreal one day, and the next day you're talking Kenya, whatever. No, you're not. But on the other hand, it does look like it's happening already, right? You are giving a talk in Montreal one day, and the next day you're talking Kenya, whatever. No, you're not. But
I can hear you.
There's some feedback now.
There is some echo, right?
Yes.
Echo.
Joachim, did you want to start? It's about 10 minutes of.
Yes, okay, so maybe we should start. So welcome everybody. It's nice to see so many people in spite of the very strange hours we have here. For some of you it's very late. Here in Catalonia it's almost 9 o'clock, so that's prime time. Soon the restaurants will open. Well, now they don't because of the pandemic, but normally that's the time restaurants would open. So we would like to apologize to Asia because it's a very bad time for Asia. It's really in the middle of the night. For example, in Kurdistan now it's 11 in the evening. Okay, but before I get on to more practical information, I would like to give the word to Brendan Fong from the Topos Institute, who will give us a short welcome. Are you there, Brendan?
Yeah, thanks, Joachim. Welcome, everyone. So I thought Joachim and David asked me to say a few words on behalf of Topos. So this workshop on polynomial functors is sort of hosted virtually by the Topos Institute. We're a new nonprofit research institute based in Berkeley, USA, where I currently am. So good morning, or good early afternoon from Berkeley. Our mission is to shape technology for public benefit by advancing sciences of connection and integration. So what this means is that we believe technologies, mathematical and computational technologies, are increasingly influential in shaping our world. This conference itself, as people were just discussing, as we all rolled in, is an example now mediated by Zoom and the internet. It's providing new ways for us to interact and sort of come together as a society. And we believe that this has tremendous power to shape the world positively, but also risks involved, as we're already seeing with, say, how technologies are influencing, say, the democratic processes. And so we also believe that mathematicians and computer scientists have a role in sort of shaping these technologies for the public benefit, to make sure they are safe, they are robust, they are equitable, they are fair. And so that's the sort of work we hope to do at Topos. One of our initial research themes is around sort of distributed dynamical and decision-making systems, and it's led by David Spivak, and our core focus is polynomial functors and ways that these can be used to these sort of applied ends. So we thought a great way to kick off this first project would be to host a nice workshop, bringing together the field around polynomial functors and setting the stage for the next few years of research. So it's lovely to see you all here. I want to thank the organizers, David and Joachim, for all the work they've done so far, and all the speakers for the wonderful talks we're about to hear. So I'm really excited for the week ahead, and welcome. If you have any questions about Topos, feel free to get in touch with me or anyone at the organization. David, of course. Valeria DePaiva is another key faculty member. Evan Patterson, Tim Hosgood too, he's helping with the tech. So thanks to Tim too. Yeah, I'll hand back to Joachim, but wishing you all a great week ahead.
Thanks a lot, Brendan. So practical informations. So as you see from the program, there's some big lines inside the workshop, such as coalgebras, type theory, homotopy theory. So maybe you are interested in one of these areas, but curious about the others, or maybe you're experts in all of them. So one goal of the workshop is to bring all all of us together and learn what people do with polynomial functors in other areas. So I think that's the goal of the workshop. In particular, we're very, very happy to have some tutorial lectures. So they will be given by Richard Garner, Helle Hansen, and David Spivak. So that's why some of the speakers speak more than once. They're the tutorials. So you can see in the schedule that it's very compressed, that we try to squeeze everything into 4 hours so that we can accommodate at least some of the most, how should I say, well, important time zones from the viewpoint of the speakers, at least. Of course, there are many time zones that we cannot favor. So for this reason, it's very compressed. So each talk is 50 minutes. Then we have 10 minutes for everything you do between talks, including questions and applause and coffee and go to the toilet and everything. So let's try to keep it strict. And regarding questions, as you will maybe have noticed, you cannot unmute yourself. But if you want to ask a question, you should just press the raise hand button. Then you will promptly be given the power to unmute yourself. You can also ask the question in the chat, and maybe that's a better way to be noticed. So these are the 2 ways to ask questions. Finally, in parallel with the Zoom session, we are running a Zulip chat. Maybe many of you know the Zulip categories chat. If you don't know, it's not so important because we have the chat inside Zoom here. But it's also possible to ask questions in the Zulip chat, and I will try to keep an eye on it in case one of the questions in the Zulip chat needs to propagate to the speaker. Otherwise, the benefit of the Zulip chat is that it continues long after the workshop is over. People can still look back at all the wonderful talks and discuss the mathematics of them. What else should I say? I have a list. Where's my list? We are recording all the talks. I don't think that your faces will appear, so you should not be worried about that. But if you ask a question, it will be recorded, of course. And if you are not happy with that, I would propose that you only ask the question in the Zulip or in the chat. Now we're pretty many. Now we are 113 participants. And there is a danger in these big meetings that suddenly we can be Zoom bombed. And if you don't know what that is, then you are lucky. But it means that there is an emergency that suddenly it can be shut down. If the whole thing shut down, then you should check your email. Then within a few minutes, you will be sent a new link. So that's sort of the emergency exit in case we are getting Zoom bombed. So in that case, keep an eye on your email. And I think that's all I wanted to say. Do you want to add something, David? Otherwise, I think we should proceed and ask André. Are you ready to share your slides so that we can prepare for the talk?
I guess so. I think I should. Just a moment. Does that work?
Not yet. Did you do share screen?
I am full screen, yes.
No.
Share screen, the green button.
Okay.
Ah, that looks good.
Not yet, huh? Just a moment. Full screen.
Looks good.
That's good.
Yes.
Okay.
Should we start? So it's a pleasure to welcome the first speaker of the workshop, André Joyal, from the Université de Québec à Montréal, who will speak about 3 kinds of polynomial functors. Please, André.
Thank you, Joachim. And I should first thank the organizer. Okay, of the workshop. Maybe I only have 2 names in there. I'm sorry about that. I think Brenda Fong maybe should be also put in the list of the organizer. And this talk is a report on joint work in progress with Marcello Fiore and Nicola Gambino. I rushed a little bit to prepare the slide, and I have improvised a little bit sometime. So I'm afraid that I could make some error. So if there are errors in the slides, they are all mine. They are not error from Marcelo and Nicola. Okay, so the goal is to prove that the category of polynomial functors is Cartesian closed for 3 kinds of polynomial functors. Actually, this category is Cartesian closed for probably maybe an infinite number of kinds of polynomial functors, but we have not tried yet to explore everything, the general result that maybe one could prove. So I will describe 3 special cases. They are in some sense closely related, but they are different. So what is a polynomial functor? That's the first question. In order to discuss that, I will first revisit the notions of polynomial and ring, because after all, a polynomial is just an element in the free ring on one generator. I mean, for a polynomial with integer coefficients. So one way to define a polynomial is to define what is a ring, and to consider to sort of construct the free rings and then discover what are the polynomials. Of course, historically, the notions of polynomial came independently of the notions of ring. I think the notions of polynomial was created or invented around the year 1000 by Arab mathematicians. They started to compute not only with numbers, but with sequence of numbers that represented the coefficients of a polynomial. And they had all kind of rules for computing with these sequences corresponding to multiplication, division, etc., of polynomials. So they really have, they had sort of the arithmetic of polynomial. Anyway, in addition to the notions of ring, we will introduce the notions of rig and a poset version and a categorical version. So in some sense, my talk will be divided in something like 4 parts: rings and rigs, and quantile and cosmoid. Okay, everybody know what is a ring, so I recall the definition. You have an additive structure, a multiplicative structure, and the additive structure is an abelian group. The multiplicative structure is a monoid, and the multiplication is two-sided distributive over the addition, and the ring is commutative if the multiplication is commutative. Okay. So, I mean, we will almost exclusively discuss commutative rings here, but sometime in the definition, I define things in some kind of general way. So we will consider non-commutative ring or something like that, non-commutative structure. But really, we want to study commutative structures. Okay, now the free commutative ring, or maybe the free ring on a set, can be constructed in two steps. This is known since a long time, of course. It was, in some sense, rediscovered by John Beck, who made a big use of that using so-called distributive law. But I will not use distributive law that much. I just observe that you can construct a ring in two steps. The first step is to construct the free monoid on a set. This is the functor M on the picture. And then the free abelian group on that monoid. And that's it. And the free abelian group on a monoid W is actually the enveloping ring of the monoid W. That actually, this is describing the left adjoint to the forgetful functor from rings to monoid. The amazing thing here is that when you construct the enveloping ring of monoid, you just need to linearize the monoid. You just need to take, in some way, a linear combination with the integer coefficient of the elements of the monoid. In particular, the polynomial ring on one generator is just the linear combinations of powers of x, as everybody knows. Now, we will work in a slightly more general situation, starting for free commutative R algebra. So if R is a commutative ring, then the free R algebra from generated by set S can be constructed in two steps. I see now here that I made a little bit mistake because I should have said free commutative algebra, because what I wrote is that R bracket S is R tensor the commutative monoid on S. So I really am looking at the commutative aspect of it. So, R tensor W is the enveloping algebra of a monoid W. And an element in R of S is, of course, a polynomial with coefficients in R and with variable xs, index s, indexed by the element of S. Okay. And then we can construct the category of commutative R algebra for R commutative ring. And I will denote this category C algebra R. And we are interested in the full subcategory of free algebra consisting of free R algebra. So free CILGR. And this category has coproduct. The coproduct of S copies of the polynomial algebra on one generator is actually the polynomial algebra on S generator. So I'm making a few observations here that I will use later. And if A is a commutative R algebra, then if you ham the polynomial ring RS into A, well, you get, as a set, you get A to the power S, because an homomorphism from RS into A is completely determined by its value on the generator. And this is why you get this bijection. Now, if you have an homomorphism of R algebra from RS to RT, then you can compose with, I should say, pre-compose with am I confused? Pre-compose with the homomorphism phi. And you get a map from a to the power t to the a to the power s, and this map is a polynomial map from the commutative R algebra A to the power t to s. I mean, if you look at the expression, you see this is a polynomial map. It's a so this is a map that can be defined only by using only the fact that you have this ring structure on A. And so you get a contravariant functor from the category of free commutative algebra to set. Now, I will introduce some notation for the opposite of a category. So I will denote C up the opposite of a category C. And if you have a morphism F from A to B in C, I will denote F up from B up to up, the opposite morphism, okay, in C up. And I define the category of polynomials with coefficients in R to be the opposite of the category of free commutative algebra. So that's a definition of the category of polynomial. You are probably familiar with this kind of construction. This category is actually the algebraic theory of commutative R algebra. And it's the algebraic theory in a sense of Linton, because I have admitted not only the finitely generated algebra over R, but arbitrary free algebra over R. So in some sense, it is an algebraic theory in the sense of Linton, but it's completely, of course, generated by its finitary part. Now, I introduce a little bit of notation. If I write O for the opposite object of the free polynomial ring on one generator, Rx, this is an object in this algebraic theory. Somehow it's the generating algebraic of the algebraic theory. And O to the power S is actually the dual or the opposite of the free R algebra on S. And then you have this formalism that if you take a commutative algebra, then a map from the opposite of A to O to the S will be A to the power S for every set S. And you get, in this way, a functor which preserves product. And it's a classical theorem since in the thesis of Bill-Lovier that there is an equivalence between the model of the theory, I mean, between the product preserving functor and the category of R algebra. Okay. Now, I want to show that in many situations, the category of polynomial is Cartesian closed. So I recall what it means for what is a function space. So if you have a category C with finite product, the function space of an object B by another object A is an object B to the power A. We're equipped with a morphism called evaluation morphism. such that the map beta, which is defined there, is bijective for every object z. And an object is said to be exponentiable if the function space b to the power a exists for every object b. And of course, an object a is exponentiable if and only if the functor product by a has a right adjoint, and a category is Cartesian closed if and only if every object of C is exponentiable. Okay. Okay. Now this can be dualized. In the category of commutative algebra, the coproduct of two R algebra is actually their tensor product over R. And you can introduce the dual notions of a co-exponential object, the co-exponential A triangle B of an algebra B by another algebra A is just the function space of B up by A up in the opposite category. So formally, this algebra A triangle B is equipped with an algebra homomorphism eta, which is sort of dual of the evaluation morphism, having a certain property with respect to every other R algebra Z. I think I made there's a misprint there. As I said, I wrote R algebra ring Z. Okay. Now, theorem. This is a theorem by Neafield, Susan Neafield, and Richard Wood in a paper, I think in 1917. They are proving a much more general theorem, actually. They ask themselves, when is it true that in one kind of variety of algebra, and they give some example, do you have co-exponential object? So, so that in the special case of classical algebra, they get that an R algebra A is co-exponential if and only if the algebra is finitely generated and projective as an R module. Okay, that's I don't know if this theorem, this theorem is completely new. In their paper, they have other theorem which are surely new. So I very much recommend you reading this paper. Okay, so we are going to look at this for different kind of algebra, but we will consider, instead of rings, we will consider rigs and quantile and cosmoi. So I'll give you an example which is kind of amusing. So let's look at Boolean rings. Recall that a commutative ring is Boolean if every object is idempotent. X squared is x for every x in R. Every Boolean ring is actually an algebra over the field of with two elements. And if I denote F2S, the Boolean ring freely generated by S, then, for example, the Boolean ring freely generated by one generator X has four elements. You have 0, 1, X, and 1 plus X. That's because there is no X squared, because the square is X. And since 1 plus 1 equals 0, then that's all you get. You have these four polynomials in some sense. Now, but you know that Boolean ring is actually the same thing as a Boolean algebra. I mean, a lattice satisfying a certain condition, complemented, etc. And by Stone duality, the algebraic theory of Boolean rings has for object the powers of 2, and for morphism, the maps between the powers of 2. So that's the algebraic theory in the sense of Lovia, has of Boolean rings. And now you can observe that this category is Cartesian closed, since look at this, 2 to the m to the power 2 to the m is a power of 2 after all. Okay, and therefore you have this nice kind of formulas for free Boolean rings. Now I can see that I made a mistake. There is a typo. That I've met up. Instead of for the free Boolean ring generated by S, I'm writing here parenthesis. Sometimes I write with angles, sometimes with no angles, so it's a big mess. So please forgive me for that. But when I write F2 bracket S around, I really mean curly bracket. I really mean the free Boolean ring generated by S. So, and so now there is an exponential, and the formula there that I wrote is just coming from this formula, the exponential formulas. Okay, so it's kind of amusing because that's it. I mean, you will see this kind of formulas will repeat again and again in this work. And so this formula is typical. It's always the same thing. So remember it. Okay. Now we need to extend the notions of ring. The first extension is to replace rings by rig. So a rig is a ring with where the additive structure is not required to be an abelian group, but only a commutative monoid. I think the name rig is a ring without the n. Huh? It's Steve Shanwell. I think the story is that he introduced that. Removing the n is like removing the negative, the subtraction, something like this. So that's a way to remember what to do if you want to remove the subtraction, the operations of subtractions from a ring. Okay, now the notions of rig is vastly more general than that of ring, since the notions of commutative monoid is vastly more general than that of abelian group. For example, you may take for addition the supremum in a poset, the supremum of two elements. This is far from being an abelian group, right? So an example is a distributive lattice. This is a rig. The addition is the supremum, and the multiplication is the infimum. Distributivity is essential because you want to have the multiplication distributive over the addition. A Boolean algebra, of course, is also a rig, and of course, a Boolean algebra is equivalent to a Boolean ring as defined before. Now we come to quantile. A poset is called a sup lattice if every subset has a supremum. Oh, okay, I have a misprint there. I said a poset L is a sup lattice if every subset in R has a supremum. Okay, oh my God. I should have written poset R is a sup lattice. Okay. Now, definition, a quantile is a sup lattice R, which is also a monoid with a compatibility condition between the suprema and the multiplication. And the compatibility can be expressed by a single equation, is that the supremum of A star B is the sup of A times the sup of B, where A star B for two subsets A and B is just the set of all product A small a small b for A in A and B in B. So a very important example of quantile, which I love very much, which I think was initially observed by Lovia, is the interval of real numbers. This is a soup lattice, clearly. And also it has a multiplication, the product of numbers, and it's a commutative quantile. It's a very important. If you use the log, you can replace the interval 0, 1 by the set of positive number, but you have to take minus log. And that's a problem because minus log is actually order reversing. And therefore, this nice object will become the interval of positive numbers, including infinity, and etc., etc. And this is what Lovier is using, but I prefer using 0, 1. Okay. Okay, now one can construct the free commutative quantile. There's notions of homomorphisms of quantile. It's in the homomorphisms of monoid which preserve suprema. And let's denote the category of commutative quantile by C quant. And the free commutative quantile generated by a poset. Now it will be free on a poset. Can be constructed in 2 steps. First, you take the free commutative monoid on that poset S. That's just the usual free commutative monoid. And the order takes the partial order are taking care of themselves when you construct a CM. So they are kind of independent. So and then you take the soup lattice freely generated by the poset X, whatever. And this free lattice is a well-known construction. An element of this soup lattice is a downward closed subset of the poset X. So an example of that is the free quantile on one generator X. It turned out to be the power set of the natural numbers. The natural number as a monoid for addition. Okay, now instead of working with quantile, we are going to categorify this. And here are 2 columns. Set and posets can be categorized with categories, functions by functors, monoids by monoidal categories, commutative monoids by symmetric monoidal categories, quantile by cosmoi. I will define in a moment what a cosmoi is, and commutative quantile by symmetric cosmoi. Okay. The terminology cosmoi may not be entirely standard. I think it was introduced by Benabou. It may be in conflict with a different use of this name. So I don't want to insist too much on this terminology. I wanted to have a short name for this talk. And I could have called that categorical rig or something like that, etc. But mathematics is difficult enough, and if we have complicated terminology, it makes it even more difficult. So this is why I decided I'm going to use a short name, but it's a temporary name. If you have a better suggestion, I would be very happy to have your idea. Okay, so what is a cosmoi? Well, it's like a quantile. So it is a monoidal category which is co-complete. You see, to be co-complete, it is like to be a soup lattice. And it's also a monoidal category, but there is a compatibility between the two conditions, is that the functors of two variables, which is the tensor product, is co-continuous in each variable. And the condition 2 is equivalent to requiring that actually the monoidal category is bi-close. I mean, tensoring with either side have a right adjoint for every object Z. What else? Oh yeah, I'm also asking that the category is presentable. That's a technical condition which is very useful, so don't worry too much about it. The important is that it should be co-complete. The fact that it is presentable, for example, implies that if the functor is co-continuous in each variable, then it is bi-close, right? So examples of cosmoi, and a quantile is a cosmos. Actually, a poset is a quantile if it is a cosmos. I mean, so the posital aspect of the notions of cosmos is the notions of quantile. And Cartesian closed category is also a quantile if the Cartesian category is presentable. And of course, Topos is a quantile. I'm sorry, a cosmos. A cosmos is symmetric if the monoidal structure is symmetric. And we shall say that the cosmos is Cartesian if the monoidal structure is the Cartesian product. And a Cartesian cosmos is symmetric and Cartesian closed. Now, an homomorphism of cosmoi is a co-continuous monoidal functor. And of course, an homomorphism of symmetric cosmoi is a co-continuous symmetric monoidal functor. And I just note that an homomorphism of topoi is a co-continuous left exact functor. It's a functor which preserves finite limits. So it is a bit stronger than just preserving product, but anyway, it is an homomorphism of cosmoi. Okay, now in order to develop the theory of cosmoi, we need a little bit of enriched category theory, starting where V is a symmetric cosmos. So V is a Cartesian closed symmetric monoidal category, which is co-complete because it's presentable. And category theory was fully extended to V categories by various people. Probably that my list is incomplete there. I'm very afraid that I may have not, maybe I should put Bob Perry there. I know that he is around. He's maybe listening. So maybe I should put Robert Perry. Well, of course, everybody knows the book of Kelly on an enriched category theory. And now the category of small V categories is itself a symmetric cosmos. It's symmetric monoidal closed. And we shall denote the tensor product of two small V categories, C and D, as C tensor T. There is also notions of pre-sheaf. You look at the V functors from a small V category C to C up to V, and there is a unida, etc., and everything works. It's just marvelous. I mean, I remember in the when I was young, I thought that the enriched category theory was kind of trivia. I mean, in the sense that everything is obvious. Okay, well, I don't know. Maybe it's not true. Not everything is obvious, for one thing, and also it's just a miraculous. It works. It just works. It's one of the greatest mathematical discovery of modern mathematics and rich category theory. It's just amazing. I mean, it's just amazing. The more I use it, the more I am amazed about it. It's just a marvelous thing. Okay. So there is a notion of a presentable V category. It may be defined in a sort of lazy way. You could say that a co-complete V category is presentable if it is presentable as an ordinary category. It's not the best way to define it, but it's the lazy way to do it. And then there is a category pres V of presentable V category and co-continuous V functors. When I say co-continuous, I mean V co-continuous V functor. And if you have two presentable V category, then the category of co-continuous V functors between the two is also presentable. It's just marvelous, marvelous. And also the category of presentable V category is symmetric monoidal close. There's a tensor product. And in other words, not only do you have this harm, but there is a tensor product. And the tensor product is the target of functors of two variables, which is V co-continuous in each variable and universal. Okay, maybe, I don't know if it's the best way to define the tensor product, but okay. There is a tensor product and it's closed. It's amazing. This thing is symmetric monoidal close. Wow. And you have the convolution product. I recall here that if you have two functors on contravariant functors on a small monoidal V category A, then you can compute its convolution, and this define monoidal structure on the category of V pre-sheaf on A. And this monoidal structure is symmetric if the V category is symmetric. Okay. That's also one of the most useful piece of mathematics. I mean, I keep reading, for example, I'm studying topology and homotopy theory, etc. People are using it all the time. I mean, all the time. Just okay. Now, a bit like the notions of R algebra make sense. There's also a notions of V cosmos. So a V cosmos is just defined like a cosmos, except that it's enriched over V, whatever definition. And a V cosmos could be symmetric, etc., etc. And I will denote the category of symmetric V cosmos by C algebra V. You see, this is the analog of the category of commutative R algebra. This is like the category of commutative V algebra. Okay. And there is a free symmetric V cosmos. It can be constructed in two steps. I mean, if you start the free V cosmos generated by an ordinary category, you just take, first you replace C by the free symmetric monoidal category generated by C. So there is a construction which take category C and construct the symmetric monoidal category on C. C is not necessarily enriched here. And then you take a contravariant functor from that to V, and that will be the symmetric V cosmos freely generated by C. In particular, if you take for C the one object category, you get the symmetric V cosmos on one generator. It's like the polynomial ring on one generator, Vx. And it's the category of ordinary functors from B to V, where B is the category of finite sets and bijection. Okay, Well, this is well known, but I need to recall it a little bit. Okay, now the symmetric V clusters constructed freely generated by a small V category. There is a similar construction, but this time you have to take the V symmetric monoidal category generated freely by a V category, and you have to take PV, the V pre-sheaf, etc., etc. So that's and here I'm recalling the symmetric monoidal V category freely generated by a category C. You know, it's very much like the classical construction when V is just the category of set. I mean, this is okay. Okay, now you have the category of I would say of symmetric V cosmos. I call that C algebra. It's like the category of commutative algebra, R algebra, but where instead of R commutative ring, you have a symmetric cosmos V. I mean, everything is kind of flowing itself. I mean, it's kind of amazing that you can move all algebra, commutative algebra, replacing a commutative ring by a symmetric cosmos V. And then what you get is you will be able to define what is a polynomial functor, yeah, because you have the free symmetric V cosmos generated by small V categories. I call that V bracket C. And everything repeat itself, so there is no point of staring at that page that long. This is just a repetitions of a page that I had written before and that you showed you before. And then you can go to polynomial. Polynomial will be the opposite. You take the opposite of this category of free V cosmos. Okay, category of polynomial. Okay. And in this category of polynomial, there is a kind of generating object, which is the object which correspond to the polynomial in one generator, Vx. So I write Vx up because it's in the opposite category, and I call this object O. And this O can be exponentiated by a small category. You have O to the C, which is just the opposite of the polynomial VC. Okay, just formally, it's just the same. And so you have a category of polynomial. Okay. Now, the category of free V cosmoi, free C algebra V is Cartesian closed. Why is that? Well, that's the formula is there, okay? The triangle between C and D is just this formula. And remember the formula for it, for the co-exponential in Boolean algebra, huh? It's the same. Well, you have to make a little bit of modification, but it's the same formula. And the proof is kind of formal, and this result was first discovered by 4 authors, something like 10 years ago, maybe a bit more. Fiore, Gambino, Allen, and Winskill. In the case where V is the category of set. And it was extended by Gambino and myself to the case of an arbitrary co-complete symmetric monoidal category. Maybe we are also presenting, supposing that it's presentable. So, but that's the formula. It's and it followed that the category of V polynomial functors is Cartesian closed. This corollary is just a rephrasing of the theorem, actually. Now, okay, that's kind of curious, okay? But is this some kind of accident, or this is something very basic and which is going to repeat itself all the time? And that's what we claim, right? Okay, so let's replace V cosmos by topos. Except that we are going to call a topos a logos because we want to look at a topos as a commutative ring instead of space. So we take the opposite of the actual of the category of topoi as it is usually defined. So you may call it a topos if you want, but I want to make the distinction, and I like to call it a logos, and Mathieu Anel and myself, we have written a paper on the logos topos duality. Okay, so now it's a very classical formula that the topos SC freely generated by a small category C is constructed in two steps. First, you take the lex completions of C, where you complete C under finite limits. This is called a lex category or lex completion. Lex for left exact. And then you take the presheaves on it. So it's on two steps. Okay, so it's like cosmoi. Now let's go to the category lex here is discussed explicitly, but I don't have much time left, so I will move fast. So you have a descriptions of the category lex, okay? I won't look at it. Now let's look at the theorem. The category, okay. I quoted the same author, but not exactly. So sorry about that. I was rushing to prepare my slide this morning. So the category of free logos is also co-Cartesian close. And here is the formula for the co-exponentiation. The only difference between the formula that we saw before is that instead of taking the symmetric envelope of a category C, we take the lex envelope of C, okay? And it followed that the category of logos polynomial is Cartesian close. Okay, now let's go to the next. Okay, now we are going to look at Cartesian cosmoi. So a Cartesian cosmoi is a Cartesian close presentable categories. It's a cosmos where the tensor product is actually the Cartesian product. And a morphism there is a co-continuous functor preserving finite Cartesian product. Okay. And again, the free Cartesian cosmos, sorry for the misprint, free, generated by a small category K is constructed in two steps. Instead of taking the lex completion, as we did in the case of topoi, we take the finite product completion. Okay. And now I think you could write the theorem, right? So the category of free Cartesian cosmos is Cartesian close, is co-Cartesian close, and here is the formula. And it follows from that the category of Cartesian polynomial, which is the opposite, is Cartesian close. Okay, so I have a list of reference. I will correct I will complete the reference. I'm sure that I can add more. I will correct my slides, and then I will give it to Joachim and David. Thank you for listening.
Thanks a lot, André. That was very nice. So now we come to the questions, and I think there's already an interesting comment from Paul Taylor. Let me see if I can figure out how to unmute Paul. If I can find him. Ah, it's alphabetical order. No. Sorry about that.
I'm unmuted. Yeah, okay. No, I just observed that that the formula a few slides back was looked like Girard's linear decomposition with a bang operator. I think that's quite common. Once you know, Girard made that observation, people in domain theory you know, found examples all over the place.
What happened? Paul, are you there?
Hello, I thought. Yes, can you not hear me?
Now we can again.
I just commented. I'm not sure I really needed to speak this. In the chat was enough. That the formula looked like Girard's linear decomposition of implication. Yes, and when you know in the late 80s, when after Girard had made that observation, people in domain theory, you know, observed that this happened rather commonly. That a lot of the domain theoretic constructions of function types we knew, you know, were of that form. That there was a bang operator and a linear thing.
Should am I supposed to say something about that, or
If you want to?
Well, yeah, I think you're right. There is certainly a connection. I mean, sure, yeah, yeah. There is a connection. There's plenty of connection. That's one of them.
So, are there other questions? Then you can either write it in the chat or raise your hand. Meanwhile, I have a question myself, because now we planned a workshop on polynomial functors, and now you come and tell us that the notion of polynomial functor is much, much more general. So we need to reschedule the whole conference. But maybe you can make a small comment on I don't know if I can say the usual notion of polynomial functors, but those where you have a map from E to B, and you take the sum over B and sum over the fibers and things like that. How does it fit into this bigger picture?
Yeah, right. One thing I didn't said is the possibility of extending everything I wrote about cosmoi to infinity categories. If you replace set by the category of infinity groupers and etc., and you do like Lurie is doing, probably that Lurie has done pretty much a lot of that already. Then, as you know, because Joachim, because of your result with Gepner, that your polynomial functors defined from a map, for example, are the same as the polynomial functors defined by symmetric sequences. And the polynomial functors defined by symmetric sequences are exactly those that give you the free algebra on one generator, if you like. And so if one goes to infinity categories, things becomes smoother. So this is something that should be done. Maybe develop this theory of polynomial functors, not only in ordinary category theory, but also for infinity categories.
Okay, thanks. And then there's a question from Steve Audi. Let me see if I can find him. Now I think you can unmute yourself now, Steve.
Okay, you could have asked it for me, Joachim. It's okay. I just wanted to know if you expect some of those examples to be also locally Cartesian closed.
Oh, it's a good question. That's a very good question. I really don't know how to do that. I think going from Cartesian closed to locally Cartesian closed, I don't see how to do that. I mean, yeah, I don't know. That's a, yeah, I would love to do that. I mean, but I don't know how to do it. Yeah.
Now there's a comment from Sam Staton that, let me see if I can unmute Sam. Sam, I think you can unmute yourself now.
Oh, hi, thanks, yeah. Oh, we showed that, I think the category of, can you hear me okay? I think the category of containers is the same as what you're calling polynomial functors, and we showed that that's not Cartesian closed in a paper.
I'm not too.
not locally Cartesian closed. Yeah.
Okay, it's not locally Cartesian closed. Yeah. Ah, okay, right. I was going to ask Marcelo Fiore to answer your questions, but yeah, actually, there is much more than what I said, because not only the category of free algebra is co-Cartesian closed, but the many non-free algebra are also exponentiable or co-exponentiable. And in my work with Nicola Gambino, we have included operads. I mean, if you have an operad, a symmetric operad, a many-sorted, then it has an enveloping symmetric monoidal category. And if you take a symmetric operad, it has an enveloping, it's a classical construction, symmetric monoidal category. And if you take the V pre-sheaf on this symmetric monoidal category, you get cosmos. And this kind of cosmos is co-exponentiable. And in my work with Nicola, we proved that the co-exponentiation between the V cosmos associated to two operad is actually classifying the V bimodule between the two. And we proved that this category is also co-Cartesian or Cartesian closed, depending whether or not you see it as a dual. So there is much more stuff to be there. I mean, the free things is just the bare skeleton of the whole thing. There is much more meat around the skeleton, and I said nothing about it.
Okay, thanks. I'm afraid we have to move on. So I think we should thank André again for this very, very nice talk. So
I thank you very much for listening. Thank you. So we had 10 minutes?
No, they're already used with all the questions. So now we move on directly to David Spivak.
Okay.
Are you ready, David?
Yes, I am. Okay, thanks.
Can you share your screen or? what you want.
So, okay, full screen. Okay, can you see it okay?
Yes.
Okay, well, thanks Joachim, and thanks for everyone for being here. And thanks Andre for your wonderful talk. And okay, so today I'm going to kind of give a tutorial on polynomial functors, at least the slightly more classical, I suppose, ones of, say, polynomials in some number of variables, things like that. Say, I usually think of Gambino and Cox's paper as the reference that I use. But the way I'm going to talk about it, or a little bit, is kind of like an abacus. So there's a story by Hermann Hesse called The Glass Bead Game, and it depicts a monastic community of thinkers led by a game master. And the game is played on some kind of instrument that involves strings of glass beads. And like some kind of poetry slam or rap battle or something, the game is played to express deep ideas, and people represent connections between math and music and philosophy by using these glass beads to weave the subjects together. And to play well means to contemplate the depths of everything and to communicate what you found. And I really loved the idea of the book, but for me, and I read it, I think before I knew category theory at all, but something was missing. Basically, Hesse only roughly describes the instrument, the sort of abacus of strings, of beads itself. And I really wanted to know what sort of combinatorial object would actually be capable of this grand scope. So to me, Poly can serve, so the subject of this whole conference can serve as an abacus. So I'm hoping to justify to you why I think that's true. And so what I'm going to talk to you about today is the theory of this thing. And then next time I'll probably continue with that, but move into applications. So today I'll talk about Poly and its combinatorics. I'll discuss some pleasing properties and monoidal structures, and present a frame by category P, which is a slight generalization of the one in Gambino and Koch. And then on Wednesday, in the second half of this tutorial, I'll recall P and discuss some more properties of it. And then I'll talk about a bunch of applications like dynamical systems, data, and deep learning, which I think is why I'm calling it, or suggesting the analogy of this abacus for glass bead game, the fact that it can talk about so many aspects of our world. Okay, so my category Poly, the one I'll call Poly today, is not exactly the one Andre called Poly, but it's the one that I think is classically called polynomial functors in one variable. And then we'll get all of the polynomial functors in many variables later on as deriving from it. So what is Poly? It has many different ways of describing it. One is the free, completely distributive category on one object. So I'm taking that terminology from lattice theory. It's got coproducts and products that can be indexed, by two different sets, and the products distribute over coproducts. It's the free coproduct completion of set op. It's the full subcategory of all functors from set to set that are spanned, that preserve connected limits. It's the full subcategory of functors from set to set spanned by coproducts of representables. And one that gives me terminology I'll use today is it's kind of the category of typed sets and collapse maps between them. So it's kind of like schemes or ringed spaces or something, but you have as objects a set I and a functor from I to set, so I many sets. And a morphism is a map from I to I prime and a natural transformation going the other way. But just because this is a tutorial, I'll start by, we'll go pretty fast, but in the beginning we'll go fairly slow. And so, and if you've seen me talk about this before, you'll probably recognize a lot of this stuff. But when I write a polynomial, I really like the notation of just basic, polynomials, y squared plus 3y plus 2. This polynomial can be represented, it has, if you plug in 1, you'll get 6, and those are the 6 dots down here. And Joachim in his question to Andre asked about maps from E to B bundles, and this is the picture of y squared plus 3y plus 2. Over this dot, there are 2 because we have a 2 in the exponent here, and we've got 3 dots with 1, and then 2 dots with 0. But in fact, so notationally, I really like this algebraic notation, but in terms of pictures and intuition, I think this one is my favorite. So we've got 6 dots here. This one's got 2 corresponding to the 2 there, etc. So for notation or for terminology, I'll call these things positions. So this polynomial has 6 positions, and this position has 2 directions. And I know that conflicts with some other terminology, and I'll get to that in a second. So this little machine here, you could repurpose this abacus to be the polynomial 15, because there are 15 columns, y to the 10, because there are 2 times 5 many ways to arrange these beads. Or maybe there's delta 4 times delta 1 if you allow for topological, more interesting separations between these beads. But anyway, so that's just a kind of funny picture that it is kind of like an abacus. You really columns of data in some sense. So here's the problem with terminology. The problem is that terminology from computer science doesn't fit my way of thinking about things. So here we have a polynomial y cubed plus 2y squared plus 1. And the terminology from Abbott and Ghani and Altenkirch is shapes and positions. So he would say that this polynomial here has, say, 4 different shapes, one with like foo with 3 y's in it, bar with 2, baz with 2, and quux with 0, y to the 0. And so each of these shapes, this one, this one, this one, this one, would have some number of positions, 3, 2, 2, or 0. But I personally prefer to think of these positions, at least when we're working with them, as projection arrows. Like this y here or this y here is really more like the projection arrow than some kind of position, at least to me. So it was a hard decision today whether to use my own terminology or to try to invent new ones, but I'm going to stick with my own terminology today, and I'll call them positions. This would have 4 positions, and the directions, there would be 3 directions here. And the reason for this decision was that in dynamical systems, which we'll get to, positions will be points and directions will be vectors, so that the terminology fits, whereas point being a shape and vector being a position doesn't fit as well. Or in categories, the positions will be objects and the directions will be morphisms. Or when we draw terminal coalgebras of these things, so very native things to do, the terminal coalgebra trees, the positions will be kind of labels of the nodes and the directions will be arrows. So I apologize to those people who use the other terminology. I know it's prior and I know it's useful, and so today I'll use this. So in terms of morphisms, how do they work? If you've got 2 polynomials like y cubed plus 2y and y to the 4th plus y squared plus 2, those would be represented this way. And a morphism is some kind of way of taking P and offering control to Q. So P says, for each of my positions here, I'm going to delegate it to a Q position, and then I'll pass the directions back. So like maybe I could delegate 1 to 1, and 2 to 1, and 3 to 4. Okay, so each of these guys gets assigned a position, and then all of the directions there are passed back to directions of P. So let's say you had to you'll either have to roll a die, or flip a coin or roll a die, and you want to delegate that to a card deck. One map would be that if you have to flip a coin, if you get the ace of, you'll ask the card deck, and if you get an ace of spades, you'll pick heads, and if you get any other card, you'll pick tails. And if you get a card 1 through 5, you'll pick that number, and if you get 6 or above, you'll pick 6. But one will, okay, so it's kind of this way of delegating from this polynomial to this polynomial. But one that's important that we'll use a bunch in this talk is, what about a map from an arbitrary polynomial to y? This is the identity functor from set to set. And what is a map from P to Y? Well, it would be a way to assign to every position in P a direction there. Because basically every position in P is assigned the unique position here, and then the unique direction here would be passed back to a direction in P. Okay, so, but the easiest description of poly is that I'm going to say it's sums of representable functors from set to set. And my notation here is that for any set S, y to the s is this functor represented by s. I'm using that so it looks familiar, like polynomials, y squared plus 2y plus 1 type thing, and but it is Yoneda of s. So a polynomial is a sum of representable functors indexed by some set, and the notation I'm using is that p bracket I is the representing set of the ith index. A morphism of polynomials is just a natural transformation. Okay, so one last thing about notation. Since a polynomial is a sum of representable functors, but I want to, this I here, I can actually recover by plugging in 1. If I plug in 1 to this thing, all these go away and I just get I. So I'll actually write this way. A polynomial is a sum over I and P of 1. Those are the positions. And in the ith position, the directions are P bracket I. So P of 1 means plug 1 into the polynomial, the one element set into this functor. And P bracket I means the representing set there. And I just wanted to quickly derive the combinatorial formula for morphisms. So I said poly PQ, how does it work? Poly PQ is poly of this sum to this sum. And because poly is a full subcategory of functors from set to set, because this is a coproduct, I guess, I can pull it out. And now I've got a representable here. And poly from a representable into something, again, because it's a full subcategory, we just plug this in for y, and we get the product over this sum with pi plugged in for y. So if reading this out, it says to give a map from P to Q is for every position I in P of 1, choose a j in Q of 1, and then choose a function from Q bracket j to P bracket I. So passing those directions back. Now I'm going to use, so I've already said I'm going to use this notation, then this notation, then this notation. Okay, this is another kind of notation I'll use today. So P of 1, I'll draw these boxes, and P of 1 will be down here, and P bracket blank will be up here. So what am I saying? The bottom part is going to be filled by indicating a position, and the top part will then be, only then can I indicate a direction in P of I. So this sort of notation gets more interesting for maps. If I've got a map of polynomials from P to Q, then this formula phi, this natural transformation from P to Q, says however you fill the blues, I'll fill the whites. So in starting Topos Institute, we have to do a lot of spreadsheets, and apparently spreadsheets put blue for the fields you're supposed to fill in and white for the fields that are calculated. So I'll put a blue for data that the formula phi needs, and then white for what it tells us. So for any I you choose, if I'm giving you a map phi, I'll return phi1 of I. I'll return something in Q of 1. And for any E, for any direction you choose there, I'll pass it back to a direction in P over I. Okay, so that's some notation I'll use to compute some of the results later on. Right, it'll really come in handy when we talk about composition. So let me just give you some pleasing aspects of poly, the category. So first of all, it contains 2 copies of set and a copy of set op. So for any set A, my capital letters will denote sets and lowercase letters will denote polynomials. But anyway, so for any set A, it's either a constant polynomial, you can think of it as a constant like 5, or a linear polynomial like 5y. And those are both full inclusions of set into poly. And set op can also be fully included into poly. Y to the power A is a polynomial, and that's also full subcategory. And all of these 3 functors I said has at least 1 adjoint. So that's 6 adjoint functors there. Poly has all coproducts and limits. It's extensive, meaning limits and coproducts work well together. It's Cartesian closed. And the coproducts, limits, and closure agree with their usual coproducts, limits, and closure in functors from set to set. 0, the polynomial called 0 really is the initial object. 1 really is the terminal object. The plus really is the coproduct, and the times really is the product. So y squared plus 2y plus 1 really is isomorphic to y plus 1 squared. And y to the a really is the internal hom from a to y. So it's all, the notation's all very, very good. For fun, I'm saying you can take any, it's Cartesian closed, so what's y to the y? It turns out to be y plus 1. Poly does have co-equalizers, but they differ from the co-equalizers in set to the set. For example, the 2 projections from y squared to y, their co-equalizer is 1, whereas in set to the set, it's 1 for non-empty sets and 0 for the empty set. Okay, poly has 2 factorization systems, an epimono and a vertical Cartesian. Epimono, you probably all know. Vertical Cartesian means that a map of polynomials is vertical if it's an isomorphism on the positions, and it's Cartesian if for every position, the pass-back morphism is an iso on the directions. Okay. There's also lots of monoidal structures on Poly. We said it has a coproduct, so it has this co-Cartesian monoidal structure 0 plus. But André mentioned deconvolution, and it can be applied to any symmetric monoidal structure on set. So if you've got a symmetric monoidal structure I dot on set, then we get a distributive monoidal structure y to the I O dot on Poly by deconvolution. In the case of 0 plus, the O plus, I guess, would be called times. But anyway, we get this product that really is the product in Poly. So y plus 1 times y plus 2 is y squared plus 3y plus 2. And in the case of 1 times, we get something that I write with a tensor formula, tensor symbol. So p times q is this, right? If I've got two polynomials p and q, we can multiply them by taking the sum over all positions in p and all positions in q of y to the sum of the exponents. And p tensor q is given by the same thing. They're both distributive, but it's p the ith directions times the jth directions. And this right-hand one, tensor, well, we already said the left-hand one has a monoidal closure, the exponentiation, but the right-hand one also has a closure, and it's given by a pretty interesting formula. So what are the internal what are the positions? What polynomial is p bracket q? Its positions are the actual polynomial maps from p to q, the natural transformations. But what are the directions given such a map? The directions there are, a direction there is a choice of position in p and a choice of direction in q at phi1 of that position. Okay. There's one more monoidal product which will be of great interest to us, namely, if you compose two polynomials, the result is again polynomial. So there, again, a kind of notational clash, I'll use this triangle to denote the composite of p and q. Of course, the typical would be a circle. If you write this fast, it'll look like a circle, so it's not a big danger there. But I use this for a bunch of different reasons, and I'll talk about them in a second. So for example, if p is y squared and q is y plus 1, then p composed q is y squared plus 2y plus 1. It's not symmetric because q composed p will be y squared plus 1. The identity is the unit. And so why did I choose that weird symbol? First of all, I want to reserve circle for morphism composition. These I'm considering as objects, so I don't want to use up my symbol there. But also, we're going to see on the next slide that p triangle q represents trees kind of growing upward from p to q. So if p is y squared plus y and q is y cubed plus 1, then we could draw p composed q by stacking q trees on top of p trees. So here we see all the ways of stacking these guys on top of these guys. And we get y to the 6th plus y cubed plus 1 plus y cubed plus 1. And so you can see it as kind of q standing on top of p with the trees growing upward. You could also read this as q feeding into p, which is exactly what composition is. So that's where that notation is coming from. All right, so let's talk about maps to composites, because that's going to come up a lot in a second. The Abacus pictures that I've talked about are most useful for them. And so if I had a map from P to Q composed R, what is that? A map phi like that is, for every position in P, a choice of position in Q, and for every direction there in Q, a choice of position in R, and for every direction there in R, finally, a choice of direction back in P, and then you stop. So let's write this with our Abacus pictures. We would write P on the left, and we write Q stacked on Q below R on the right, and our phi would be this kind of cobordism-y looking thing here. So what did it say? It says that in order to, for what phi does, it says for any I provide, phi will provide some j in Q of 1. And for any E I provide in Q bracket j, every direction there, phi will provide a k in R of 1. And for every F in R brackets k, every direction there, phi will provide a D, a direction in P of I. So that's how this kind of, how a map from P to Q composed R looks in the in this picture notation. This is what I'm calling the abacus. I'm not really sure what I'm calling the abacus. But anyway, in this very combinatorial way of drawing things. And these will come in handy when we ask whether two, like a phi and a psi, are equal. So when I say all this is going to come in handy, I mean now. So in any monoidal category, you can consider comonoids. A comonoid in MI tensor is an object M called the carrier of the comonoid, a map from M to I called the co-unit, and a map from M to M tensor M called the co-multiplication. And in Poly, the comonoids are exactly categories. So this was a result of Aman and Ustalu in 2016. And in some sense, this whole talk is an advertisement of their result together with Richard Garner's results, saying that bimodules are parametric right adjoints, but I'll get to that in a second. So how are comonoids in Poly exactly categories? Well, if C is a category, what's the carrier of the comonoid? It turns out it's this thing here. So its positions are the objects of C, and for every object in C, the directions there are the outgoing morphisms, the set of morphisms in C that emanate from I. And you write down that polynomial, and that has a comonoid structure. The co-unit, if you remember what a map from C to Y is, it is for every object of C, or for every position, a direction there. In other words, for every position, every object of the category, I need an outgoing morphism. And it turns out that the rules of comonoids, the laws, will force that this thing has to assign the identity. And the co-multiplication delta from C to C composed C turns out to assign codomains and composites. So when I heard that comonoids are categories, I was totally astounded and shocked, and very, very happily, of course. When I told a bunch of people about it, they all thought that was, I told Richard Garner and oh no, he already knew. I told Mark Weber and Todd Trimble, and they thought, well, that's not so surprising. But for me, it was very surprising. I'll say why they didn't see it as so surprising later. Their explanation helped me understand it better. But let me say how I understand this result combinatorially. Because again, I'm working with this kind of abacus of set theoretic polynomial functors, and there you can just watch the things go around. So if you have a comonoid where C goes, where you have a co-unit like this, and a co-multiplication like this, the first unitality law says that identity of C triangle epsilon composed delta is identity of C. Okay, so what is that saying? If you read out the laws of comonoids, what does the first one say? It says that whenever I fill in this bottom thing with an I, okay, I fill it in both spots, I run the abacus. I draw these double arrows, by the way, to just mean equals. They're not natural transformations, they're just equalities. They just mean copied over. So, okay, I run this thing, I hit it with delta, I get delta 1 of I here. Whatever delta 1 is, whatever these maps are that define this co-multiplication, I know that this thing is delta 1 of I, and yet it's supposed to be I. So I get an equation, delta 1 of I is I. And now for any F that I fill in there, I get F over here, but I get some crazy formula over here. And the crazy formula says, you know, this map applied to F and blah, 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 blah equals F. And so the abacus here is letting us check their result, but it wouldn't have gotten us their result. Aman and Ustalu's result or Richard Garner's result, which we'll get to in a minute, the insight for it is required because these crazy like formulas that like this, if you don't know how to interpret delta and epsilon, et cetera, you might not notice that this is telling you something very familiar. So to make sense of these equations, what I'm going to do is rename epsilon sharp delta 2 and delta sharp. I already know that this one is identity because that was the easy part. Okay, so let's write IDY for epsilon sharp. Let's write cod for delta 2, and let's write compose for delta sharp for this thing here. So with that renaming, then the previous equation, this terrible looking equation here, simply says that F composed of the identity on codomain of F is F. So it's telling us something, well, I mean, that's pretty familiar. And then the other unitality equation gives that the codomain of the identity on I is I, and that the identity on I composed any F is F. So it tells us a lot about identities and their codomains. And then the associativity condition says that the codomain of F composed G is the codomain of G, and that F composed G composed H is F composed G composed H in the other order. So here's how that looks. So you draw this big abacus picture, or I was calling these poly boxes, but you draw this big picture. You see these two different cobordism looking things here. You fill it in. I'm just going to write it all out. You put in an I, and the first thing you find is that I equals I. And so that's no data. And you run it again, and you find that codomain of F equals codomain of F for any F you plug in. That's no data. But then when you plug in G, you run it through here, you get F composed G, because that's what this thing is supposed to give you. You take the codomain, you copy it over, and you get codomain of F composed G. Whereas if you go this way and you take G, you just get his codomain. So we get this equation. And finally, we plug in, we take an arbitrary H, and we get this equation. And so these polybox things can help you if you want to prove these things from first principles or just set theoretically. They just organize what you need to know. So even though comonoids in poly are categories, the maps between them, the comonoid maps, are not functors. They're called cofunctors. So what is a cofunctor from a category to another category? Well, it's a polynomial map, first of all, and then it satisfies some rules. So for every object in C, we get an object in D. Let's call the object I in C. You have a cofunctor from C to D. For every object in C, you get an object in D, so it goes forward on objects. But then for every morphism emanating from that object in D, you get an emanating morphism from I in C. So you pass the morphisms backwards. And the rules, if you read off what the comonoid morphisms should do, phi sharp, when it passes back morphisms, it should preserve identities, it should preserve composites, and phi, the forward direction thing, should preserve codomains. So it still preserves identities, composites, and codomains. It's just that they go in different directions. Let me write cat sharp to denote comonoids in poly, categories, and cofunctors. Up to isomorphism, by the way, sorry, both cat and cat sharp agree on what an isomorphism is, what an isomorphism should be. Cat sharp has no idea why you'd think equivalences were important. But okay, anyway, so what's a cofunctor from C to the rationals? So here's the monoid of rational numbers. It's got one object, and it's got rational number many morphisms. And so what's a cofunctor like this? Well, it would be trivial on objects because this only has one object. But when you pass back morphisms, basically for every object in C and for every rational number, you get some kind of morphism from I to something, let's call it I plus Q, that emanates from I for every rational. And the rules would say that phi sharp of 0 should be identity. So in other words, when you plus 0 to an I, you get I. And second of all, that when you compose the morphism you get for Q, and then you run it again on the new thing with Q prime, it should be Q plus Q prime. So basically what that's saying is it's giving you a vector field on C in some sense. Every object in C, or it's kind of giving you an integrable vector field. It says it, for any object in C, you give me a number, 23, and I'll move you forward 23 units of time. And if I then move you forward 5 more units, that'll be 28 units from the original thing. So it's a pretty strange sort of structure to put on a category. A cofunctor from C to the rationals is like a big vector field on C. It's a whole new world to explore. If someone asked me whether functors or cofunctors are more important, to me it's obvious that functors are more important. I mean, they're the basis of category theory, and they're obviously essential to all of math as we know it so far. But I once heard Richard Garner say maybe one day we'll think cofunctors are as important as functors, or that they are. That was really surprising to me. But of course, I mean, I respect Richard a lot, and so it's really interesting. I mean, how interesting are cofunctors? They're certainly weird, and they give you a whole new world to explore. Okay, so here are some examples, just so you get a sense of how these comonoids, or what polynomials kind of underlie categories. So note, if you have a category underlying, if you have a polynomial for a category, then that polynomial never has a constant part. every object needs an outgoing arrow, and so you don't have like y plus 3. It's always divisible by y. So it's actually linear. The polynomial is linear if C is a discrete category. Because every object needs an outgoing identity morphism. The polynomial is representable if and only if that set carries a monoid. And really, I'm saying that the monoid structure on the set is exactly what you need to define a co-monoid structure on the representable there. But here's one just for intuition, I guess. If you have this category, the corresponding polynomial will be y to the n plus y to the n minus 1 plus dot 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 to y. So this thing has n outgoing morphisms, one to itself and one to every other thing, and this one only has one. Here's some other facts about categories and cofunctors. So coproducts in cat sharp and in cat agree. Their carrier is the sum of the polynomials. Cat sharp has finite products. A student working with me named Nelson Yu proved that. They're very interesting things. For example, if you take the walking arrow category with n equals 2 here, and you take the product of it with itself, that thing has infinitely many objects in cat sharp. Product in cat sharp. Finally, cat sharp inherits a monoidal structure from poly. And so when you take the tensor product of two categories or comonoids, it's the usual categorical product of those categories. Just multiplies objects and arrows. Okay, to any polynomial P, we can associate the co-free comonoid on P. So this is the forgetful functor from cat sharp to poly has a right adjoint. And I'll give it an explicit description of this on the next slide. I must be talking fast because I'm moving faster than I expected. Okay, so there's a standard construction for this type of thing. I think it's in a paper of Porst, and I don't know how common it is, but anyway, we need a polynomial for any polynomial P. I need a polynomial CP and maps from CP to Y and CP to it compose itself. So what do? Starting with a polynomial P, we first add a copoint. We first get this thing by just multiplying the polynomial by Y. So PY, the product of P and Y, is the universal thing that maps to P and to Y. So that's the universal copointing. And then we get this, we get the comonoid we need by taking the limit of this diagram. So what is this diagram? There's a map from Py to Y that's just projection. This is P times Y. So you can just take the projection onto the Y variable, Y factor. Or Py composed Py, I could either take this side and project it onto Y and get Y composed Py, which is Py, or take this side and take the Y factor and get Py there. And so you just take the limit of this big diagram, and that will be the co-free comonoid. Now for us, a main use of this thing will be that there's an equivalence between P coalgebras and functors from CP to set. So if you have a coalgebra from S to PS, so P is a polynomial, S is a set, S to PS is a coalgebra, and that corresponds to a functor from CP to set, from the co-free on P to set, and the elements of this functor. So every functor from a category to set has a category of elements, and the set of elements of that will be S. So when you think of functors to set, Poly seems to like to think of those as their set of elements equipped with a CP, equipped with a co-algebra structure on this comonoid here, but from this comonoid here. But I'll get to that later. So for example, if you take CP of 1, if you take and I don't mean the complex projective 1 space, but if you take the co-free comonoid on P and plug in 1, then you get the terminal P coalgebra. Why? Because the terminal P coalgebra would correspond to the terminal functor from this thing to set. And the terminal functor from this thing to set, if you look at its category of elements, would just be the objects of this thing, which is CP of 1. Okay. So if comonoids in Poly are exactly categories, then the co-free comonoid on P is a category. Which category is it? So you've got a polynomial P and you're getting a category out of it. Which one do you get? It turns out that that category is free on a graph, but the graph is really very interesting. So the co-free comonoid on P, its vertex set of that graph is the set of P trees, which I'll define now. So what are the vertices of this graph? A P tree is a possibly infinite tree or non-well-founded tree T, where each node in that tree is labeled by a position of the polynomial. So you've got a tree labeled by positions of the polynomial, and when you have that label, the number of branches there is the number of directions, the set of directions. So here's an example object. Here's an example tree where P is 2y squared plus 1, or in other words, yellow, comma, green, y squared plus red. So here's an example of one object in this category, CP1. So every node is labeled by a color, green, yellow, or red. And when it's labeled by green or yellow, it's got 2 arrows coming out of it. And when it's labeled by red, it's got none. Now I picked a very particular tree here, but any tree where the nodes are green or yellow or red, and where the greens and yellows branch twice and the reds branch 0 times is a object in this category or this graph. Okay, what's a morphism in this category or in this graph? If you've got a tree that's an object, what's an arrow emanating from it? It's just a finite path through this tree. So this whole thing is an object, and if I go through the tree to some other node, that's a morphism, and the codomain of it is the tree that's sitting there. That'll again be a P tree, and so that'll be my morphism. So objects are these P trees, morphisms are just paths through the graph, ending up somewhere else. The codomain, I said, is the tree sitting there. The identity is the root node, the 0 length path. And if I have a path from this one to this tree, and I have a path in this tree up to this tree, then the composite is just the path to this subtree here. But it's nice to imagine this entire graph or this entire category, okay? Because this is just one object. This graph has every possible destiny. So in other words, imagine that at any point you're either in the green mood, the yellow mood, or the red mood. If you're in the red mood, you never get any more information ever again. But if you're in the green or the yellow mood, then you'll either get a left or go right, and you'll go into some new mood. So the way that you in particular transition through moods as people give you left and right directions, they give you the direction, move left, move right. The way you do that is your particular destiny. And every possible destiny, every possible tree like this is in there, and as an object. And when you look at that object and you look at all the arrows coming out of it, you see the tree itself. So it's at once, it's like a crystalline, very like crystalline structure, and also completely free. Everything is in there. Okay, so by comodules in Poly, when I said this talk was in some sense an advertisement of Amina Ustalu's result and Richard Garner's result, we're getting to Richard Garner's result here. So given categories C and D, or comonoids, we can read off from the typical definition, you can find in NLab or whatever, of what a bimodule or bicomodule between them would be. And what is it? It's just a regular old polynomial, positions and directions, and 2 morphisms, one to C composed M and one to M composed D. And of course, they have to be a bimodule or bicomodule, they should cohere with the comonoid structure of C and D. So in other words, if you go from M to C composed M, and then you go from C to Y, you would get a map from M to M, and that should be the identity on that polynomial M. So all my lowercase letters here are polynomials. It's just that these C and Ds are math frac because they also have a comonoid structure. So for the notation of this, I'm going to look at these. We see M repeated 3 times in the middle here. And then we see this like kind of triangles both going in the same direction. So I'm going to write the comodule bicomodule like this. So we've got C and D, we've got M between them, and then we've got these triangles. So I'll say this is a bicomodule between C and D. And the triangles at the end help me remember how the maps go. They go from M to C composed M, and from M to M composed D. Now, maybe this direction looks like it's going the other way, but I think this is the op that André had in his talk. I'm not 100% sure. But the point is, why does it seem to go from D to C, even though it's a CD bimodule? Well, Garner, so you can look this up, Garner's hottest polynomial video. Here's a link, but the slides will be available later. So Garner explained in his video that bicomodules between C and D, which we've denoted this way, can be identified with parametric right adjoint functors, which I'll call prafunctors. Parametric right adjoint functors from D set to C set. If you don't know what a parametric right adjoint functor is, at least in this case, they are exactly the ones that preserve connected limits. I've been talking about, I said connected limit on the very first slide, and it's coming back again. Okay, so from this perspective, as a functor from D set to C set, it does appear to go in the correct direction. So you can either think of this in the kind of combinatorial direction, that's like a CD bimodule. When you think of a polynomial as a combinatorial object, I tend to think of it as going this way. When you think of it as a functor, I tend to think of it going this way from D to C. So let's just assume we believe Garner's result for a second, and we'll get to it with the Abacus pictures in a second. But assuming his result, let's just check that the C0 bimodules are equivalent to C set. So the C0 bimodules, according to this result here, would say that they are the parametric right adjoint functors, the prafunctors, from 0 set to C set. Well, 0 set is the category of functors from 0 to set. And there's only one of those, because 0 is the empty category. So it's the parametric right adjoint functors from a one element category to C set. And every functor preserves connected limits. Every functor from 1 to C set preserves connected limits, so we get this result here. So in other words, we're getting all these Coprey-Sheaf toposes C set. Every Coprey-Sheaf topos in the world is in this, is a category of bimodules, namely from C to 0. So prafunctors generalize profunctors. This is slightly abusive because the profunctor goes from C to D, whereas the prafunctor, although I'm writing it this way, it really goes from D set to C set. So, but prafunctors from D set to C set generalize profunctors. How so? A profunctor from C to D, at least in my personal preference of direction, is a functor from C op times D to set. And moving the ops around, that's a functor from C to D set op. So that's a profunctor. D set op is an important construction. It's the free limit completion of D. So it's saying that every object in C gets a formal limit in D. A profunctor is like a profunctor, except it goes from C to the free coproduct co-completion of D set op. So given an object in C, we get a coproduct of formal limits in D. So that's profunctors and prafunctors. If you wanted to prove, so again, the insight, Garner's insight that this is bicomodules, that bicomodules are prafunctors from D set to C set is amazing, because working this out, you just get a whole bunch of formulas. But you can write them all out using these Abacus pictures. I mean, you just put boxes here, you'd run things around. You'd get these pictures, you'd check things, and you'll get a bunch of formulas. And I just invite you to do it if you're interested. You'll just find that it works out. So by running the Abacus and interpreting the results, we find a bunch of different things. For example, a left comodule from M to C composed M can be identified with a functor from C to poly. So if you have any functor from C to poly, any category you want, and a functor to poly, that would be a left comodule on that category. So what would you get if you had this thing? We would take M, and we could write it as the sum over all objects in C of a sum over some new set. I write M sub I. So all of the things in here that went, all the positions in M that went to the I object in C would be Mi of of the representable y to the m bracket x. Okay, so what we're saying is that a left comodule can be identified with a functor from C to poly, and then the right comodule conditions say that each m bracket x, each of these guys, is not just a set, it's the set of elements for a Coprey sheaf on D. So each of these guys is actually a Coprey sheaf on D. And then when we add the coherence condition, by which I mean this one here, that says that if you do rho and then lambda, it's the same as lambda then rho, it kind of just makes the functoriality work out. So the idea is that every position in C, every object in the category C functorially gets some set Mi, and each element of Mi gets a D set with whose element is m bracket x. So you just take this polynomial m, you write it out in a different form, and you see all the parts of it as the parametric right adjoint. So how does this work? If you want to get the parametric right adjoint, the Praf functor from D set to C set, what it does is it takes a D set n, it homs in all of these m bracket x things, all these Coprey sheaves m bracket x, into that D set, and then adds them all up, and you get a C set. So we'll understand this better semantically when we get to applications. Let's see, let me just look at what I've got here. Okay, I think I have time to do just one or two more slides. So here are some facts to get you acquainted with this thing. If D is 0, if your bimodule is here, then the carrier must be constant. The bimodule equations tell you that this has to be just a set. And that'll be the set of elements of our Coprey sheaf on C. And if m is constant, it always factors through 0. So if you have a bimodule between C and D, and it's going to be a polynomial, if that polynomial is constant, it factors through 0. Okay, so here's another thing to say. So I've already said that the C0 bimodules, the constant left C comodules are C sets, but there's a lot of things that are C set. The Cartesian cofunctors over C, or the discrete op vibrations over C is C set. But I guess more interestingly right now, if you take the linear left C comodules, those are C sets, and the representable right C comodules are C sets. So if you've got a bimodule, if you've got a module whose polynomial part is linear, my, then that will correspond to just a Coprey sheaf on C. A representable right C comodule is also just a Coprey sheaf on C. And Gambino-Cox frame by category of polynomials between where you have like a set of polynomials in many variables, we get by just looking at the discrete subcategory, the discrete categories inside of P. So P here is the category of categories, cofunctors, and bicomodules. And if we just look at the discrete categories, we recover the Gambino-Cox frame by category. Now, if you've ever tried to compose by Praf functors, you might remember a diagram that looks like this. If these are all discrete, then these commas just become pullbacks. And so you get this kind of, you have a bridge diagram like this, another bridge diagram like this, and you form a pullback, and you form a comma square, another comma square, distributivity pullback. But what's really amazing to me, the reason I think of this abacus is it's so combinatorial, is that to compose two bicomodules, m and n, what is the answer? You just take the usual, you just compose m and n as polynomials, and you compose m, d, and n as polynomials, and you take the two maps between them and you take the equalizer. So anyway, so that's, I don't have a wrap-up slide for today. Tomorrow or Wednesday, when I come back with the tutorial, I'll talk about a little more about that stuff, about bicomodules, and then I'll get to applications. But I think I'll stop here for questions.
Okay, so we can thank you Wednesday. So right now, let's go directly to questions. Let me see. So there's a question from Callum Reader. Does anyone know how nice cat sharp is? Do you get anything unitary with cofunctors?
Do you get anything unitary with cofunctors? I guess I don't know how nice cat sharp is. As I said, it has products and coproducts. I think it has all co-limits. I don't know if it has all limits, but I think, Nelson, you told me that it does. I don't remember for sure right now. But I don't know what we might want to know about Yoneda. Maybe I'll just say I don't know what to say there.
And then there's a question from Frederick Quintanar asking what's the significance of these trees not being well-founded?
Oh, I just meant that, yeah, I just meant that they're not, they might be infinite. They might go on forever. That's all I meant there.
And then Richard raises his hand. Richard, I think you can unmute yourself. Or do I need to do anything?
Oh, you might.
Hello.
Oh, great.
Thank you, David. That was a very nice talk. So just a little question. So if you take the bicategory of profunctors, you can obtain that from the bicategory of spans by completing in a suitable world under Kleisli objects or something like that. So I just wondered if you'd thought about whether the same thing might be true here. So I start with the bicategory of polynomials, and then I can try and adjoin Kleisli objects in a suitable world, and maybe we get this bicategory of PRA functors between small categories.
Yeah, so if you take the profunctors from C set to set, that is I think that's a two monad on categories. So for any category C, I'll take the profunctors from C set to set. And I believe that the Kleisli category, I'm not sure if this answers your question, but it has some of the same words. The Kleisli category of that, I think, is the horizontal category that I've been talking about today.
All right, so you're saying there's a two monad on cat, which
yeah, size issues aside, yeah.
Slightly bicategory. Okay,
right.
I think that's a different question, but equally interesting answer.
Yeah, I don't know about completing profunctors to profunctors in the way you said.
Okay, thank you.
Okay, sure. Okay, I was just checking to see if I had something about anything you were talking about, but yeah. So should we take a break or should we?
Sorry, I was muted while I asked the question of Luis Alberto Gomez. Sorry about that. So he asks, how do comonoids arise in applications?
Okay. So next time on Wednesday, I'll talk a lot about applications. But how do comonoids? Well, I mean, comonoids are categories. So if categories appear in applications, then comonoids do. But I guess cofunctors are not functors. So, so they're much less familiar. In some sense, cofunctors are a lot like vector fields. If you have a cofunctor from C to D, one way I like to think about it sometimes is that it's like a D-shaped stencil on C. It's like every object in C gets some kind of name from D, some object in D. And then the morphisms in D tell you a shape inside of C that you'll see there. So it's kind of like, yeah, I don't know how to say exactly how they show up in applications, except in a minute when, or next time when we get to talking about them. But I think vector fields, a cofunctor from C to the monoid will kind of be, well, let's say the rationals or the reals or the integers or something will be kind of a vector field on your category C. Every object, we kind of went through that earlier, but I don't have too much to say now.
There's one more question, if you can hear me, yes. It's from Konstantin Lindström. He asks, so if cats are comonoids in poly, dare we guess that bimonoids in poly are monoidal cats and Hopf-monoids provide duals?
Yeah, so if you take tensor inside of, so you can take any two categories and you can take their product as categories. And that monoidal product also exists in cat sharp, but it's not the product there. Still, you could ask, what are the monoids for that tensor product? And they're not monoidal categories. They're really interesting things. I don't know how to think of them exactly, but for any two objects in your category, you'll get an object. So that's like the tensor product. But now given a morphism emanating from that tensor product of objects, you can split it up into a morphism emanating from the first and a morphism emanating from the second. So it's like you combine objects, but you split morphisms. I didn't catch the part about what did he say, Hopf something, but or maybe I even missed the question itself. But did that answer the question? Bimonoids. Oh, I haven't looked up. I did think about bimonoids briefly, but I didn't get too far. I don't know actually what bimonoids in poly are. I think I answered a completely different question just now. But I mean, it feels to me, just to be clear, there's a ton of interesting questions to ask about this stuff. Part of what I wanted to do today is say, here's some stuff that I know about poly, but I have lots of questions. And so if someone wants to think about what bimonoids in poly are, I certainly encourage it. I'd love to know.
The first problem is that this was for the composition product, right?
Oh, right.
It's not symmetric.
No. So monoids in poly are more like operads, and I'll talk about that next time. They're generalizations of operads. Yeah, I'll talk about that on Wednesday. I kind of, yeah. Well, who knows? Okay, I don't know. I'll just say I don't know.
Could we get a copy? Could we get a copy of your note of your?
Oh yes, certainly, certainly.
I mean, on your site or something. I mean,
all the speakers will hopefully send their slides, and we'll put them on the website, and maybe I'll also send them around.
I think it would be good if you can so that we can have access to your slide right after your talk, and maybe etc. You see on time. I mean,
sure. I'll at least send it to the speakers now, and I'll put it on the.
Because sometimes it's good to think about it right after your talk, right?
It's true. Yep.
So I need to think about these notions of cofunctors. At the moment, I don't understand it.
Okay.
Okay, but now maybe you get a chance, because now Richard is speaking. I don't know if you get the chance now or maybe later. But in any case, I think we should move on. We have 1 more minute. Richard, are you ready? Maybe at least we should see if your slides are.
Oh, Richard, you're muted, by the way, in case.
Okay, I think I'm now unmuted. Is that correct?
Yes, we can hear you.
Good. And I'm just attempting to share my slides. Just need to give it a moment. Can you see anything? No. Not yet?
No.
Okay, let me try that again.
That looks like it's going well.
Well, this is problematic. I'm going to have to do some boring tech things probably to try and fix this. The iPad has just suddenly decided that it's unwilling to connect to the Zoom session.
No problem.
Okay. I'm going to blame the iPad and try and restart it and see what happens.
Sounds good.
Actually, why don't I go hell for leather and just leave the session and shut lots of things down and then restart them and see if that helps.
Okay.
I will leave and return very shortly.
Okay. Are there any more questions for David or for André? Well, that was fast. He's coming in already.
Looks good. We see your screen.
And now you can hear me as well.
Yes.
Yes.
Amazing. All right.
Okay.
IT
Okay.
101.
So
All
it's
right.
a pleasure to welcome Richard Garner. We'll talk about polynomials in categories with pullbacks. So that's the first of a series of lectures. Go ahead, please.
Thank you. And sorry for the delay. I'm pleased that I managed to resolve it in the end. So I'm talking about polynomials in categories with pullbacks. Okay, so these are a tutorial series of talks, which means that if you're an expert, and there are many experts here, you may want to snooze lightly through this first talk. Although, I mean, the main thing that I found difficult in preparing this is correctly attributing all these ideas. So if you feel like telling me that you proved something which I've attributed to someone else, then please do, because I'm sure I'm going to get some portion of the history wrong here, but I'll do my best. So, okay, so I'm going to just present to you two different views on polynomials. So David's told us about polynomials in set, and my goal is to tell you about how the theory of polynomials in set generalizes to other categories. And so I'm going to start with what you might call the operational view on polynomials. I guess you could also call this the extensive view. Okay, so what's polynomial functor? There are lots of ways you could define it, but I guess originally a polynomial functor from set to set is one that's in the closure of the identity functor under finite product and finite coproduct. Okay, so that generates a class of functors, which is naturally called the class of polynomial functors from set to set. Okay, and I guess more generally, I could close the identity not under just finite products and coproducts, but under arbitrary products and arbitrary coproducts. Okay. And if you do that, then you get precisely the things which are in this category poly that David described. So things that look like polynomials, but where the exponents may be infinite sets and where you may have an infinite sum of such infinite monomials. Okay. So more generally, I can talk about a multivariate polynomial. Polynomial functor going from set to the I into set. And that's one in the closure of the projection functions from set to the I to set under, again, all products and all co-products. Okay. All right, and so those correspond to, I mean, what in algebra you would think of as a multivariate polynomial. So like x squared y plus y cubed x, or something like that. Okay, and even more generally, a polynomial functor from set to the I to set to the j is just a j-index family of polynomial functors from set to the I into set. Okay, and of course the reason that you would consider this last case is because then it's obvious how to compose polynomial functors, right? So you could think that right, if I want a category of multivariate polynomials, then I can't compose something from set to the I to set with something from set to the j to set, but I can compose a j-index family of things from set to the I to set with something from set to the j to set. And that is captured if I use this final notion of polynomial functor. And so this is what's normally meant by a polynomial functor on set. So this is a sort of generalized or dependent polynomial functor on set. Okay, and so these are the things that I want to talk about subsequently, these things here. Okay, now the thing is, there are many other views on such polynomial functors. I might just bring up the chat so that if there's anything that immediately arises that I can answer as I'm going, I can see it. Okay, there are many other views on polynomial functors. So, and I'm just going to list a few of them. And to be clear, I'm just going to be looking at functors from between pairs of sets for the moment. Although actually, to be honest, I'm going to replace immediately pairs of sets by slices of set, because as we know, set to the I is equivalent to set over I, the slice category set over I. And in general, it's kind of nicer to work with set over I because that's easier to generalize to other categories, as we'll do in a minute. Okay, so I might call this, I'm going to put a 1 in the margin here so that I can start my numbering here with 2. Okay, and so I guess this is very similar view, right? So I can look at functors from set to the I to set to the j, which are composites of set over I, sorry, to set to the j. So I could have a delta f. So here f is a function from j to I, and so this is I guess delta f is pullback along f. Okay, and pullback along f has 2 adjoints. It's got a left adjoint and a right adjoint. Okay. Does anyone have any problem with green and red? I'm just going to continue using them if no one says that there's a problem with that. Okay, so the right adjoint here is generally called pi f, and the left adjoint is called sigma f. Okay, and so these are quite easy to describe. Well, at least sigma f is easy to describe. Sigma f is just post-compose with f. and pi f is dependent product. Okay, and maybe I could spell out what pi f does. So, I mean, maybe the easiest way to think of this is as follows. So pi f, and for the moment, let me just describe it in terms of something from set to the j into set to the I. Okay, so I'm just going to go backwards and forwards between this slice view, etc., and the power view. So this is a family of sets that's like aj for j in j. Okay. All right. Now, I guess really what I want to do is not think of it as a family of sets indexed by j, but first of all to break up j to I and think of j as a family of sets indexed by I in the first instance. So I'm actually not going to do that. So first of all, we're going to say here, let's say where I'm going to think of f j to I as giving the family of sets j sub I for I and I, with j sub I equal to f inverse of I. Okay, so I think of f as presenting a family of sets ji for I and I, and then a family of sets indexed by j can be seen as a family as follows: a family A, I, j, where I is in I and j is in j of I. Okay. All right. And what do I send that to? I'm going to send it to a family of sets that's indexed by I in I. So a family of sets indexed by I and I. And what does that family of sets look like? Well, it looks like product over j in ji, aij, indexed by I in I. Okay. All right, so that one's a little bit harder to describe than the pullback and the post-composition functors, but you can see what its essence is, that it just takes some big product of a family of sets. Okay. Now, if you presented sigma f in a similar way as a function between powers rather than between slices, then you'd get basically exactly the same formula, except that that product would be replaced by a sum, a co-product. Okay. So it just happens that there isn't this a similarly nice description of pi f just as something like post-composition, but this element-based description is pretty straightforward. Okay. All right, and so you can imagine that a composite of stuff like that is going to give me something that is built using pi's and sigmas, and in fact, you get everything that you can build using pi's and sigmas starting from the projection function. So this gives me the same class of maps. Okay. All right. So another view is that they're functors from set over I to set to the j of a very special form. So they're actually of this following set form. I can go from set over I to set over E to set over B to set over j. And I guess the point is that there's some particular order in which I do this. So first I do a pullback, then I do a pi, and then I do a sum. So this is delta along some map T. This here is pi along some map P. And then this last thing here is sigma along some map S. Okay. So clearly 3 is a subclass of 2, but the magic is that actually they're the same. And what's even more magic is this is going to remain true when we generalize to an arbitrary E in a minute. Okay. All right, and so then let me mention a few more. So far it's been like, okay, I generate a class of functors by taking some stuff, but I also have completely intrinsic characterizations of this class of functors. So functors set over I to set to the j, which preserve connected limits and are small. Okay, small just means that they're a small co-limit of representables, and that's just a size condition. But then this condition of preserving connected limits is super important. And so these are basically what Girard called normal functors. So, I mean, he, I think, had preserves filtered colimits rather than small, which is a stronger condition. But more or less, this is the notion that Girard came up with. So there's all sorts of interesting stuff that Girard did on this topic, and kind of related stuff that sort of dips in and out of linear logic. But it's quite a fun body of work to read, actually. So I mean, okay, so I guess even earlier in the sort of French school, we have the notion of a functor from set over I to set over J with a left multi-adjoint. So we all know what left adjoints are. So I'm not going to tell you what a left multi-adjoint is, but this is a theory that was developed by Dier at the end of the 70s. And I guess picked up again by various people sometime later. In particular, I might mention functors which, let's say, whose slices so let's call this functor f. Functors whose slices, so if I got a functor from C to D, I can slice it over an object of x, or an object x of C, to get a functor from C over x to D over fx. And so that's what I mean by the slice of a functor. And so I can look at functors whose slices are right adjoints. Okay. And so a name for this, I'm not claiming that this is where the notion originates, but this name, local right adjoint, I think was, introduced by Ross in 2000 in the paper Petit Topos of globular sets. And these are closely related to the things that that David was talking about, the parametric right adjoint functors. So I mean, more or less the same thing if your category has a terminal object. I mean, they are the same thing if your category has a terminal object. So parametric right adjoint functor is one whose slice f over 1 is a right adjoint. Okay. All right. So we've got all these different characterizations of polynomial functors between slices of set. And so it's natural to say, what happens if I take all of these and I generalize them to not set, but a nice enough category E? If I generalize these from set to E, okay? So, I mean, there's no problem in doing this, right? So each of, I mean, okay, well, no, there's no problem in doing this. For each of these, there's an absolutely obvious interpretation of what we should mean by interpreting this in set. So I can take 2 and I replace set with E. And then I certainly have pullback functors along morphisms if my category E has pullbacks. And then those always have these left adjoints sigma f, and under nice enough conditions, they'll have these right adjoints pi f. So that will make sense. So 2 and 3 are fine. Connected limits, perfectly good notion. Works for any category we want. Similarly, these other notions are just completely generic. And so we can just naively replace set with E throughout and see what happens, right? Okay, well, what does happen? Well, it depends a bit on what E is. But typically what happens is that 4 is equal to 5 is equal to 6. So that's kind of being very crude. So if, for example, E is locally presentable. So I mean, in some sense, that's a strong condition, but in another sense, it's quite a reasonable condition. And that's, I mean, that's too strong. I mean, I don't think you need that quite that strength for 4 or 5 and 6 to coincide. But I mean, it's basically kind of the difference between them is something to do with like a solution set condition or something like that. So you might as well think that those are kind of more or less the same. Okay. So then obviously we have, so 3 is clearly contained in 2 always. But note here that pi f from E over I to E over J may not exist. Okay, so in a general category E, it's not a priori the case that these pullback functors delta f, which we can define perfectly well, may not have right adjoints for all f. So we can restrict to the class of exponentiable f, which by definition, these are the f for which pi f exists. So I've managed to write a few lines there with no content, you might notice. So I'm saying that pi f might not exist, but if we restrict to the f for which pi f exists, then pi f exists. But the point is that these maps are called exponentiable, okay? All right, and then, so one is kind of not very much to do with the rest if I generalize to an arbitrary E, except that one is contained in 2 if E is extensive. Okay. All right. Maybe I should say l'extensive. So I'm not going to explain that, but I mean, I need a terminal object and coproducts of the terminal object, and then I can kind of embed polynomial functors in the sense of 1 into polynomial functors in the sense of 2 and 3. Okay. All right, so there's kind of these 3 classes I've mentioned, and I've sort of split them up like that. Typically, so I mean, what we have is that let's say this. So the relation between, I'm going to ignore 1 subsequently, but if I look at the relation between these two things, so these are the things involving pi's, sigmas, and deltas, and here the things which are kind of to do with preserving connected limits. So the pi's, sigmas, and deltas always preserve connected limits. So kind of things of the form 2 is contained in 4. Now in set, it happens that these coincide, but typically what happens is that inclusion is strict. Okay? And so you get these sort of 2 different theories. Now the theory of 4, 5, and 6 is super interesting. Okay? So for example, when E is a pre-sheaf category, so I'm going to say a few words. So 4 equals 5 equals 6. Typically super interesting. So if E is a pre-sheaf category, we have the PRA functors that David talked about. So if E is a variety, you get some quite interesting things happening. In particular, you get things called co-rings and friends. And I don't know, plethories is another word that's sometimes used. Okay, and so this is sort of been studied by a bunch of people. I mean, in the more general context of an arbitrary variety, so Tall and Wraith, and George Bergman has really done a lot in this vein. Bergman and Hausnecht have got a fun book about this kind of stuff. And André has done things about this. And Jim Borger at ANU is a big, so here in Australia, at Australian National University, Jim Borger is a big proponent of co-rings in algebraic geometry. And so there's all sorts of interesting stuff there. And so here's another interesting example. If E is sheaves on X, where X is a I don't know, let's say a stone space for simplicity. Then looking at these functors of the kind 4, 5, and 6, you get stuff that's related to topological dynamics. Topological dynamics and combinatorial C-star algebras. Or I say non-commutative geometry, that's probably the easiest way of saying it. Geometry. Okay, and so the point is it's very dependent on E what this theory looks like. So the point is however 2 and 3 give a much more uniform theory which is the theory of polynomials. The theory of polynomial, I mean, it's typically termed the theory of polynomial functors in E. Okay. All right. Now, the amazing thing is, and this is quite amazing actually. So I didn't tell you how it was that kind of 2 and 3 coincided in set. And if you do the analysis, it basically comes down to the fact that there's a infinite distributivity between sums and products in set. Okay. And the thing that's sort of almost magical is that if I generalize to an arbitrary category E, you might think maybe I need some extra properties on E to get the equivalence between 2 and 3, which would be a reasonable thought. And the magic thing is that in any category with pullbacks, the classes 2 and 3 coincide. And so I guess this is really the thing that makes this a theory rather than just a bunch of definitions. So the magical fact is that in any category E with pullbacks, two and 3 coincide. So I guess my goal is going to be to try and explain to you how that works. Okay. And so why? Well, basically because things in 2, remember 2 is just the closure under composition of all the sigmas, pi's, and deltas. And the point is that things in 2 have normal forms in 3. 3, remember, is something which is a delta followed by a pi followed by a sigma. Okay, and so so I can attribute this to various people, I guess. So I guess the version where this is done in full generality for the first time is in Gambino and Cox's paper in 2013. I fear this might not be true, but I'm going to at least say that it's true. Okay. So that's for a category where all the pi f's exist. So a locally Cartesian closed category, one where every map is exponentiable. However, in a category with pullbacks, this was done by Mark Webber in 2015. Okay, so what's the idea? Well, the idea is basically we're going to rewrite stuff. So if we've got a bunch of composites of sigmas, deltas, and pi's, we might have them in the wrong order. Like we'd like to have delta followed by pi followed by sigma. So if we have something that doesn't meet that expectation, then we just want to rearrange stuff until it becomes in that form. So I guess there's 3 things we might want to rewrite in order to do this. So if we have, so suppose I go as follows. I'm in E over I, and I'm going to go into E over J via a sigma f, and then I'm going to go into E over K via a delta G. So I do a sigma f followed by a delta G. All right, so I'm in a category with pullbacks. So maybe I should make that, I think I've already said I'm in a category with pullbacks. Okay, so I'm in a category with pullbacks. I've got a pair of arrows like this. I mean, I can't stop myself really. I take the pullback. Let's call it L. And then I get a pair of maps here, U and V. Okay, and so maybe I can draw my F and my U in green just to attempt to follow this pattern I seem to have established. So I've got F and U. All right, so this is just a pullback. Okay, I can form pullback to the right. And now, so the 2-cell, so I got a 2-cell just from functoriality of Pullback that tells me if I start in E over J, I'm going to E over I, and then going to E over L. And on the other hand, I can go from E over J to E over K to E over L. And so this is just pulling back along everything in sight. So I go delta F, and then I go delta V, or on the other hand, I can go delta G and then delta U. So there's an invertible 2-cell there. So that transposes using the adjunction between the deltas and the sigmas. So that transposes to a 2-cell like this. So I've got E over I here, and I can go down to E over J. So I do a sigma along F first, and then I do a pullback along G, taking me into E over K, I guess. And on the other hand, I could first, starting in I, do a delta along V, taking me into E over L, and then do a sigma along U. Okay, and so there's a 2-cell in here, happens to point this way. And that turns out to be invertible. Okay, and so that's the Beck-Chevalley condition. That's what it's called. You can just prove that that 2-cell is invertible. All right, but now we're good, because that tells me that I start in E over I, going to E over J, E over K. So I'm doing a green followed by a black. Then I can actually rewrite that as a black, delta V, followed by a green. So that takes me to E over L, followed by a green, which is sigma U. Okay, so I can rewrite. And so I push the black thing to the left of the green thing. And similarly, I can do, so if I've got E over I, and now I do the same thing, but rather than a green thing, I'm doing a red thing. So I do a delta G, but I'm doing this after a pi F. So, oh, that's not a pi, that's a sigma. Okay, I'll do a pi F. All right, so I got that. Then I can form this pullback. So I guess it's the same pullback, except I'm going to colorize it differently. I've got K, J, L, I, and here I've got G and V. And then here, going down, I've got F and U. So that's the same pullback square as before. And the canonical 2-cell obtained by transposing in a similar way, but using the adjointness now of the deltas and the pi's. So the canonical 2-cell I get, I guess it's the same one, but pointing in the other direction kind of thing. So I got E over I, delta V, E over L. Here I got E over J, E over K, and this is delta G. All right, and then going down, I can do now pi along F. And I can do pi along U. And now I've got a 2-cell, which I guess goes this way. And that's again invertible. And so that gives me a way of rewriting this lower edge as its upper edge, and therefore pushing the black arrow to the left of the red arrow. And so this is again a Beck-Chevalley. So we can rewrite. Okay, so remember the order we're trying to get is black, red, green. So far I've got enough stuff to push in any composite of blacks, reds, and greens. I can push all the blacks to the left now, all right? So now I've just got to get the greens and the reds in the right order. And the problem is if I have a green followed by a red, I need to rewrite it in some way such that I can kind of push all the reds to the left of the greens. So that's the final case we need to consider. And okay, so far there's nothing that's kind of particularly controversial. So kind of Beck-Chevalley, I mean, it's kind of old stuff and fairly, I mean, it's well-established stuff and kind of completely reasonable that you might have these isomorphisms. So I guess all the magic is in this part 3, which is that we can always do this rewrite here. So if we've got E over I, all right, so I've got E over I, and then I do a green into E over J, and then I do a red into E over K. So this is sigma along, apparently this is F, and then this is I along G. So we need to do a rewrite, and now this rewrite turns out to be more complicated. Okay. Oh, I guess I should say something, right? Here. So here, there's something I skipped over. So I got F, I pull it back to get U. Now the thing is, I'm supposed to take a pi along U. And on the face of it, I don't know that U is piable. I know that F is exponentiable, but I would like to know that U is exponentiable. But happily, exponential maps are stable under pullback. And so there's no problem with this. So I should write that down, but I'm not going to. But just in case you're worried about that, this is exponential because it's a pullback of an exponential map. Okay. All right. So let's return to what I was saying. So if you've got this picture here, then we can form the following diagram. So I've got my map F. Let's try and do the colors in a sort of consistent way. So I've got my F, which I'm supposed to be summing along. And then I'm pieing along this map into K here. Okay, now I've said that the map from J to K, namely G, is exponentiable. And therefore, I can pi F along G. So this is an object in the slice over J. And so I can apply my pi G and get an object in the slice over K, which I guess I'm going to call, well, I suppose I should call it pi G of F, but I'm actually then going to subsequently call it V. Okay. All right, so I have an object here, which seems to be called M. All right, and now I can pull that back. I'll call that map U, and I get another object here, L. And then I get a map here, which I'm going to call epsilon. So why do I get a map there? So this is the co-unit of the adjunction between pi G and delta G. So this is co-unit. So this epsilon is the co-unit of delta G left adjoint to pi G. And this is pi G is going from E over J to E over K at F. So F is an object in E over J, and so I can take the co-unit and that object, and it's a map between F and the pullback of the pi of F along G, and the pullback of the pi of F along G is L, and so I get this map epsilon into I over J. Okay. All right, and so this is a commuting square. So this left composite here is the pullback. Okay, so I'll call that square star. All right, so now by messing around with adjoints, so using the Beck-Chevalley isomorphism for this pullbacks for pi's in this pullback square. So I start from the Beck-Chevalier isomorphism for pi associated with this pullback square, and then I mess around with some adjoints, some transposing basically. And in this way, I get a canonical 2-cell of the following form. So basically what I do is I've color-coded these things, and so I start in E over I, and then I follow around the top path by pullback, pi, and sum, or I can follow around the bottom path by sum and then pi and see what happens. All right? And so I have E over I. I can pull back along epsilon, taking me into E over L. Then I can, it seems, pi along U, and that takes me into E over M. And then I can sigma along V, and that takes me into E over K. On the other hand, I can first sigma along F, sigma F, and that takes me into E over J. And then finally, I can pi along the remaining edge G, and that takes me down into E over K. All right, now it turns out that there's a canonical 2-cell filling that square. And I guess the magical fact is that that 2-cell is always invertible. Okay, and I should say in set, this invertibility expresses the isomorphism between the following things. So suppose I take pi over A in A, sum over B in B, depending on A, of CAB. Yes, as Torsten says, this is the type theoretic axiom of choice, and I might describe this as such in a moment. So this isomorphism says if I take a pi of sigmas, I can rewrite that as a sigma of pi's. And how do I do that? Well, it's a sigma over, so I've got a function which takes an A in A, returns a B in BA, and then a C in CAB, where the B is the B I just chose. And so I can rewrite that as first a function that takes an A in A and returns a B in BA. So that's an F in pi A in A, BA. And then for each A in A, I return an element of CAFA. Okay? And so I could call this the type theoretic axiom of choice. Or if I was a lattice theorist, I don't have to be a lattice theorist, but if I was inspired by lattice theory, I might call this complete distributivity. Okay, so a completely distributive lattice is something that satisfies this condition with meets and joins. Okay, and so in general, and so the amazing thing is that this, although we don't have anything that's sort of directly to do with sigmas and pi's knocking around, sorry, that's nonsense. Although we don't have anything that's directly to do with sums and products, we have these sigmas and pi's, which are somehow kind of internal manifestations of that in E. And without any assumptions on E, it's always the case that this thing is invertible. Okay. All right, and anyway, the point is, so using the invertible star, we can rewrite so I guess if I got a green followed by a red as, well, it seems to be black followed by red followed by green. Okay, and that's good because that's the sort of order that we're after in the end. Okay. All right. And so using these three rewrites where you can turn any 2 into a 3. So my notation here is not perfect. Remember, 2 is any composite of sigmas, pi's, and deltas, and a 3 is a composite in that particular order of a delta followed by a pi followed by a sigma. Okay. All right, good. So I guess that's more or less all I have to say, but maybe I'll just finish with a remark. So, well, okay. Let's say it like this. So in general, we have that well, maybe not in general. Typically, we have that 2 is equal to 3, which is strictly contained in 4, which is equal to 5, which is equal to 6. So these things, remember, 4, 5, and 6 were to do with things like preserving connected limits, whereas 2 and 3 were to do with being built up in a certain way. So you might wonder if there's a formulation of 2 equals 3 in general, which is, if you like, top down in the sense of 4, 5, and 6, and in that you start from some functor and impose some properties on it such that it becomes of necessity polynomial. And turns out there is. If we interpret 4 equals 5 equals 6 less naively in E, we get another equivalent formulation of 2 equals 3. Okay, so namely, if we look at indexed functors between indexed slice categories of E. So I'm viewing E as a category indexed over E, and in that context, I can take the indexed slice category. And if I look at indexed functors between indexed slice categories of E, which in a suitable indexed sense are local right adjoint, then we get exactly polynomial functors. Okay, so there's a sort of prehistory of this. So, I mean, the idea of viewing polynomial functors as indexed is quite old. So I guess it goes back to the work of the containers people. So in particular in Abbott's PhD thesis, the view on polynomial functors is they should be seen as kind of index functors. But I think the actual result that I've just stated here is in Koch and Koch. Don't have a year. Find a year. 2013. Okay, and so basically the point is, if I look at indexed local right adjoint functors, those turn out to be polynomial functors on E, which is quite nice because, I mean, you'd like to have some kind of completely intrinsic characterization of the class of polynomial functors, and this gives you it. And although this perspective is sort of optional when it comes to describing polynomials themselves, when it comes to describing the morphisms between polynomials, the appropriate morphisms between polynomials, it's kind of more or less mandatory to observe that you have this extra structure of the polynomials. the polynomial functors, because the appropriate maps between them are the ones that preserve this extra structure of being either an index functor, or another way of saying it is an enriched functor or a strong functor with respect to E. And so, although you can develop the theory in ignorance of the fact that polynomial functors are indexed, it makes your life incredibly difficult. And so I guess next time I talked about the operational view. So next time I'll talk about what you might call the combinatorial or the intensive view, which says, well, if I got this normal form, why don't I just use these normal forms to represent my polynomials rather than the functors themselves? And so we get this representation of polynomials as these diagrams of 3 arrows. But that is a story for a couple of days' time, and I think I'll stop there. Thank you.
Okay, so we can thank you when you finish everything. So we move directly on to questions and comments. Yes, so I didn't see who was first. Let's take Paul Taylor first. So, sorry, I have to unmute you, or ask you to unmute. Paul, can you unmute now?
Can't start my camera. Trying again.
We hear you now.
Right, okay. Now it's too late in my time zone for me to take part in much discussion on going to bed at the moment. So I know you have some references from the 70s, like André, and possibly some other people, and a lot of references from the present millennium. But there were people doing this kind of thing in between those in the 1980s. So maybe it would be worth going back and seeing what those people were doing. There are other ways of looking at these functors. So my preferred one was as a something like a factorization system. And well, I'll put in the chat the web page for my contribution on this subject, and leave it to you to look things up.
Yeah. Yes, thank you, Paul. You're definitely one of the people that I should mention in this context, and I agree. There are a bunch of people between that early work that I mentioned in the late 70s and kind of this millennium.
Francois Lamarche, for example, did as well as me did a lot of things at the same time as me.
That's right.
Peter Johnston has a couple of relevant papers that's a bit earlier than me.
That's right. So there's Johnston and Carboni. They've got some papers on familiarly representable functors, and that's definitely relevant here. I mean, it's very close to these notions.
Well, also other things. There's Peter Johnston wrote something about Girard's dilators and about the S. What are they called? Disjunctive theories.
Yes, that's right. So I mean, Girard has this paper on normal functors, and that grew out of this work on dilators, which I think is amazing. I think it's if you haven't read this Girard paper on Pi1-2 logic, then it's really amazing. So it's about using parametric right adjoint functors to represent ordinal notation systems on the category of ordinals and strict order preserving maps. And I think this is just a really beautiful paper, and so I really encourage people to have a look at it.
Yeah. Well, I recommend starting with Peter Johnston's paper on the same subject, and then you might have some chance of understanding Girard.
Yeah. Okay. Thank you, Paul.
Thanks.
Okay, I'm going to now.
Maybe I can just make a small comment. So in my paper with Nicola Gambino, we list, I don't know if they're exactly the same 6 viewpoints, but it's very similar. And we also tried to be very careful with the history of this stuff. So I think if you look in that paper, you can find I think all the names you mentioned here are also mentioned in that paper. I don't know if we got everybody, but we made an effort at least, and we talked with Peter Johnston also. And
yes. So as I said, my I guess my time to prepare these talks was a bit limited, and the thing that suffered most is giving an adequate account of the history. But as Joachim says, I think his and Nicola's paper is a great source, not only for the theory, but also for the history of that theory, which is long and complicated.
I also wanted to mention that in the CT in 2010, I sat down with Peter Johnston, and he helped me draw an amazing map of the prehistory of polynomial functors. But unfortunately, that map is lost. But I mean, there was a big map, and there was lots of names, not exactly about polynomial functors, but about precursors. I'm sorry, I cannot give more information than that, but we should get hold of Peter Johnston again and sort it out again. Okay, Torsten, I have to unmute you.
Okay.
Sorry.
So host muted me, it said. Okay. Just maybe it's a very naive question, but in the beginning, you start with sort of, I mean, families of sets, I would say. And then you sort of look at, like, what I would say, an inverse image. But isn't this potentially problematic because we may have an index structure and we don't want to look at all morphisms, but only the well-behaved ones? But
right. So, I mean, this is then getting towards kind of what we do in type theory. We only pull back along certain maps, and we only, well, we can pull back along all kinds of maps, but we only sigma and pi along certain maps. So certainly, right. So, I mean, when I said you're in a category with pullbacks, I said you only take the pi's along the exponential maps.
Yes.
Now, of course, that's a, I guess there are two aspects, right? You can either say, I don't want the whole slice category.
Yeah, that's a bit
much. And then you can also say, I don't want to pi along all possible maps. So I guess there are two different axes there along which you can generalize it. So you can say, I don't have the whole slice. Sorry, so which one are you?
I'm more concerned about slicing about all maps. I mean, this. I mean, there's obviously this locally Cartesian closed categories we had before, and there seem to be always a bit too much for my taste.
Right, right. So yeah, so I mean, one kind of useful level of generality is I take a category E with pullbacks and a certain class of exponential maps, along which I'm going to allow my middle maps of my pi's in my polynomial to only be pi's along those maps in that given class. So that class, I guess, needs to be closed under composition and stable under pullback, but that's all you need. So if I just take a category E with a class of maps satisfying those properties, then I can define a class of polynomial functors where I have all sigmas and all deltas and just pi's along those special maps. And that's quite useful, I think.
Okay, thank you.
Are there more questions? Nicola says he may have the map. Valeria.
Can you hear me now?
Yes.
Great. So yeah, I kind of read somewhere that that you, Joachim, have some extra notes on polynomial functors. Is that available now, or is that, I mean, is that the same map that you are talking about, or
no, the map was a physical map, like a tree or a graph or something.
But the notes are available somewhere.
So I have some long notes on my webpage, but I mean, they have not been updated for more than 10 years, and a little bit outdated, I would say, but they're there.
Great. I think the thing that I wanted to understand a little bit more, and I hope that the next tutorial of Richard, it was a brilliant talk, Richard. Thanks very much. But the thing that I want to understand is a little bit more about this business of the type theoretical choice, or kind of, you know, the relations of the type theoretical choice with the things that one, with columnization in general. And I think, you know, kind of trying to bring back the more logical perspectives. That was my question to André already, was about, you know, whether the algebraic structures that he was playing with had to have some meaning, kind of more logical meaning, the same way as this Richard's discussion about how to alternate conjunctions and disjunctions, kind of getting him this type theoretical axiom of choice. You know, what else can we say about it? Kind of, I mean, I want to, so the real question is, how much of this type theoretical choice is given to us by the Beck-Chevalier condition, and how much is actually kind of something else, something more algebraic?
Right, right. So, I mean, I hope I will say something that maybe will answer that a little bit. So it's to do with looking at fibrations that have this distributivity property. And so then very clearly you see the distinction between the type theoretic axiom of choice, which always holds. And then if I look at a fibration of subobjects, then it turns into the real axiom of choice. And so then you can, I don't know if that answers your question, but it's somewhere in that direction of saying what's the link between this and kind of the logical principles we would normally call the axiom of choice.
That's great. Thank you. Kind of looking forward.
Okay, maybe we should move on. David Gepner, David G, are you ready?
Yeah.
Hi.
I should be able to share my screen, I guess. I'm okay. Looks like it's having a little bit of trouble.
We can ask Richard how he solved his. Maybe it's a different problem.
Maybe it's just a little slow, but.
Okay, so it's a pleasure to have David Gepner, who will talk about analytic monads and infinity operads.
Right, well, thank you for the invitation to speak at this very unique workshop. So I just wanted to get this title down, sorry. This is all joint with Joachim and Runa Haugseng. And what is the idea of this project? Well, as André said in his talk, you can of course study polynomial functors in various generalizations of ordinary category theory, like higher category theory. So we decided to do that, and then it became apparent that this would give a good model for infinity operads. So we decided to write a paper where we studied polynomial functors in infinity categories and use our theory to get a different model for infinity operads, one that emphasizes the monadic perspective. So let me give a little sketch of what we do, starting with some background. So I don't think people have brought up operads yet, so I'm going to start with a little background on operads. Not very formal. I mean, what is an operad supposed to be? It's supposed to be something which encodes algebraic structure. But maybe what do we mean by this? So algebraic structure should be somehow finitary, as in the operations we want should only involve a finite number of inputs and ideally one output. And the other thing that I want to mean by this is another thing that we sort of demand universally from a good algebraic theory is something like the ability to take resolutions of things. So I'm going to also demand that we have some notion of free resolution. And I'll put this into context later. But if I didn't ask that, what would I mean by that? Well, let's suppose that it will take some base category, and it'll be a very specific category, but I'm going to call it S. And what is S supposed to be? S can be what could be sets, or the infinity category of spaces, which is the higher categorical version of the one category of sets. Or you can take things in between, like n truncated spaces. If n were 1, you would be talking about groupoids, etc. And of course, this category has to have good properties. I mean, it should be a topos or something like that. Minimally, it should be locally Cartesian closed. But I'm specifically going to focus on the case where S is spaces, but if you prefer, you can think, if you prefer to think one categorically, you can think of S as sets. Although then some of the statements get a little messier, also, as André mentioned in his talk. Okay, so then an algebraic category would be some sort of monadic functor. I'll call it, I don't know, P lower star, monadic functor. What would that mean? It means that it has a left adjoint, P upper star. I'm writing the left adjoint on the bottom. I apologize, such that the associated monad, I'll write A for the monad, P lower star, P upper star. You know, this should be algebras for that monad. That's basically what you would probably is the most radical notion of a sort of category of algebras. But we want this to be somehow finitary and also have something like free resolutions. So let me just mention, we have Lurie's version of the Bar-Beck theorem. And I'll use a simplified version where I just talk about geometric realizations or co-equalizers instead of the split one that actually is the real content of the Bar-Beck theorem. So, you know, the functor P lower star from this category A to S is monadic if, and well, this, you can get an if and only if statement, but I'm just going to say the if statement just to simplify things a little bit. So first condition is you would want this to preserve geometric realizations. And again, you can talk about split realizations if you want the if and only if condition. And I want this to be conservative it should detect conservative. It should detect equivalences or isomorphisms. Rather, equivalences or isomorphisms in A should be detected down in S. I want to think of this as this having this free resolution property that I was talking about. The fact that it preserves these realizations, which you can think of as a higher categorical version of like a co-equalizer. It's a free presentation of something, or you can think of it that way, as a presentation. And well, if additionally, like I said, we want some finiteness, then we can also ask that P lower star preserves filtered colimits. And you'll note that filtered plus realizations implies that all sifted colimits are preserved. And I'll tell you what a sifted colimit is in a minute, because it's such a great class of colimits. If I might be mistaken, but I think this notion of sifted goes back to Joyal as well. So definition, a category C is sifted if the diagonal C into C cross C is cofinal. And that's an extremely useful class of diagrams, especially to take colimits of in algebraic situations, because what it really means is that a sifted colimits in these algebraic categories are computed underlyingly. And that makes, that's really what makes everything work here. Okay, so what does that mean? So what that means is that really we're interested in sifted colimit preserving monads. And I'll call the monad A, and it'll go from, at least for now, from S to S. And just a remark or a simple observation is that S, at least if you take spaces, but it's true one categorically too. S is the sifted colimit completion of fin. What is this? This is the category of finite sets. So if I take finite sets and I adjoin all filtered colimits to finite sets, then I just get the category of sets. So the content of this statement is really that if I add in sort of formally geometric realizations to the category of sets, I get the category of spaces. That's an informal way of stating a deep theorem. It's sort of intuitive because probably most of you know that you can represent a space or a homotopy type by a Kahn complex. So it is in some sense a simplicial set. But this is really a homotopy invariant way of making the same statement. And also another remark, this is the starting point for the Clausen-Schulze approach to the infinity category of spaces, which they call animated sets. For them, if you have a category C, and the animated version of C is the sifted colimit completion. And they get really a lot of mileage out of this. But again, just taking finite sets formally adjoining sifted colimits gives us the infinity category of spaces. Okay, so that's what monads have to do with this story. And if we want our monads to look like the sort of free, forgetful monads that come up in algebra, we want our monads to commute with sifted colimits. Okay, so now the next step in this game is to try to understand operads. When you say operads, there's always some confusion. Do I mean one categorically? Do I mean infinity categorically? Do I mean operads with just a single object? Or do I mean operads with various colors? I'll comment on exactly what I mean by that. Eventually we'll get the whole category of infinity operads as well, certain types of monads, which we'll call analytic monads. And of course, this is the analytic thing will tie in to the theory of polynomial functors. We'll see that being analytic is a special case of being polynomial, because as in Richard's talk, he said that there are lots of different types of polynomial functors. You can allow exponents which are arbitrary. We're trying to deal with algebraic categories, so we just want exponents which are finite sets. So it's a strange choice of terminology, but analytic in this setting is a special case of polynomial. Okay, so how do we do that? Well, what is an operad? More specifically, well, historically, I guess someone mentioned today that it was really Kelly who figured this out, but it is, at least in the one object case, and you can have operads with many objects, and we'll get to that later, but it is an algebra object in symmetric sequences. Now, symmetric sequences is a very rich category. It's the functors from, let me write it like this, the disjoint union over n of the classifying spaces of the symmetric groups to our category S. This is, of course, equivalent to the product of functors from B sigma n to S. And this data this is the data of a space. I hope everyone can see this highlighting color. A space with a sigma n action, an action by the symmetric group on n letters. So I specify for each n a space with a sigma n action. But there's a lot of different monoidal structures on this category. So I want to do the composition one. I'm not going to spell out exactly how that goes. You can look it up for yourself, but that's what gives you all the axioms for an operad. You start with a symmetric sequence, you ask for it to be an algebra for the composition product, and you can read off the axioms for an operad from that. But let's think for a minute how such a gadget would give you a monad. So we'd rather, at least for the purposes of this talk, we'd rather view operads as certain types of monads. And let's take the classic example. This is usually called the symmetric monad or the commutative monad, but for the purposes of this talk, I'm going to call it the exponential monad. And if you prefer, it is also sim, because the formula is the same. You take the disjoint union over all n of x to the n, and I quotient out by the action of sigma n. And I'm doing this in S. So if S really is the infinity category of spaces, I mean the homotopy quotient by sigma n. So this is the main example. This is what is called the E infinity operad as well. But I'm calling it the exponential function because it's obviously a categorification of the usual exponential function, e to the x, which is the sum of x to the n over n factorial. So this is in fact what I really wrote down. This is really the free functor, or really the free functor composed with the forgetful functor, so the monad associated to the operad. I didn't say why this is a monad, but you can work that out either combinatorially, or there are various ways of doing it. You can check that sim x is equivalent to the space of finite sets equipped with a map to x, which helps you understand its monadic structure. Okay, so but is this the type of monad we want? Does this preserve sifted colimits? So in fact, this monad evidently preserves sifted colimits because, well, all the individual terms do. It's the composition of functors which do. The subtle part is the functor that takes x to the nth power. I mean, taking the disjoint union over something is an example of a colimit, So that's going to commute. Modding out by the action of the symmetric group is a quotient operation. That's going to commute with colimits. So it just so happens, basically by the definition of sifted, that the diagonal map is cofinal, or you could take, 3 times the diagonal map to deduce that's cofinal, that sifted, the functor which takes X to a finite product of copies of X also preserves sifted colimits. Okay, so certainly that functor does. For a similar reason, for the same reason, the functor, I'll call it the endofunctor, associated to a symmetric sequence. Let's call it f of x. That would be my symmetric sequence where I have a bunch of spaces Fn going back up here for all n, which carry actions by the symmetric groups. I'm going to take the product of Fn with the nth power of x and mod out by sigma n. This also preserves sifted colimits. And as you can see, it will come equipped with a natural transformation to, to the exponential of x, because this is the one associated to the terminal symmetric sequence, where all the Fn's are just a point with their sigma n action. Okay, so in fact, it turns out, so a theorem of, I think it goes back to Tom Leinster probably, but presumably someone can correct me if I'm wrong, but it basically identifies operads with monads equipped with a Cartesian natural transformation. I'll call the monad A to emphasize that it's an algebraic object. What does Cartesian mean here? So here, Cartesian means basically that, well, I can evaluate this on any x and then apply the natural transformation. And, well, I could do the same for y, although by the rules of pullback, I really just have to check that for y being the terminal object, that this is a pullback. Okay, now what does that mean about the structure of A? We have formulas for this. So this is the disjoint union over n of point mod sigma n. So those are the classifying spaces B sigma n. This is the disjoint union over n of x to the n mod sigma n. Okay, because A sits over this, this is going to be a disjoint union of some spaces an. And similarly, we can just decompose AX as into like monomial terms like that, just because, I mean, B sigma, the disjoint union of B sigma n has a natural number's worth of connected components. So anything living over it must have at least those same components. Okay, but this is a homotopy pullback, moreover. So if I take notice that if I just look at this map and I take the fiber over, well, this is a connected space. It doesn't really matter what base point I take. You can calculate that this gives me a space, which I'll just call Fn, equipped with the sigma n action. And you can identify as An with the quotient Fn by sigma n. If I take the fiber in the vertical direction, I just get x to the n. Since this is a pullback, these have the same fibers and these have the same fibers. So if you think about it carefully enough, what you conclude is that A of x has to be analytic. It has to have a power series expansion. It ends up looking like the disjoint union of Fn cross x to the n mod sigma n, where, you know, Fn is a space with the sigma n action, and, you know, here we use the diagonal action. So just sort of from abstract considerations, we can deduce that all the monads that come from operads have to look like power series. And that's why we call them analytic monads. Okay, so also in Richard's talk, now notice, well, maybe I'll skip that part for lack of time. Okay, so let me get into some theorems then. So at least infinity categorically, this can be made precise. So this is, I'll attribute this to Leinster, and then some precise infinity categorical version appears in the paper that I wrote with Haugseng and Koch, which is that an operad is a monad equipped with a Cartesian natural transformation. I was going to call it A down to the exponential function. Okay, and then this implies, for the same reason as we discussed before, this automatically implies that A preserves sifted colimits. Okay, and now, so we get an equivalence of categories, I can look at, if I, maybe let me say it this way, forgetting the monad structure, and only considering the underlying endofunctor, well, we can get an equivalence of categories. So I want to look at analytic endofunctors. Those are exactly the ones that have power series expansions. But I want to look at the ones that come equipped with a map to the exponential, such that that map is Cartesian. So I've just described a category for you. They're the analytic endofunctors of S equipped with a map to the exponential endofunctor, which is actually Cartesian. This is just equivalent to the category of functors from, well, I'm not requiring any monad condition. So this is just equivalent to functors from fin to S, and which, as in Richard's talk, is the same as S over fin, or, you know, is a symmetric sequence. And what that implies is that, you know, I said this before, so there's a composition monoidal structure on symmetric sequences. Just because what I wrote on the left, well, it's pretty clear that we know how to compose endofunctors of S. Okay, so there is some composition monoidal structure on this, which makes the symmetric sequences, I mean, for which the algebras are the operads. And, well, I guess what I want to say is, well, let me launch into then a couple of theorems about this. So the first theorem that we prove in this, or one of the main theorems that we prove in this paper is, well, okay, I guess I should make a remark before I state this theorem. So let's also forget about analyticity for the moment. And consider arbitrary polynomials. As we learned from Richard's talk, those all can be represented by one of these bridge diagrams. And I want to consider polynomial functors of many variables. So here you can think of I and J as sets if you want. They're the sets of variables that we're going to consider our polynomials in. as Richard remarked, it's sort of enough to take J to be a point, because a polynomial functor of many variables, well, as he said, if J is not a point, we can reconstruct this whole thing by just fibering over the individual fibers of J. And I'll call this map F, this map P, and this map Q. So the associated polynomial functor is, what do we get? It's the functor F. Maybe I should say where it goes to and from. So from S over I to S over J, given by f of x equals, well, what do? I first pull back x along P, then I push forward along F in the right adjoint to P sort of way, and then I sort of add them all together via the left adjoint Q lower shriek of Q lower star. So this is the dependent sum. This is the dependent product. And this is just the pullback, to go back to that notation. Okay, so I just wanted to say that briefly, forgetting about analyticity, so I can state the first theorem relevant from this paper with Haugsing and Koch, which is the following are equivalent. For a functor f from S over I to S over J. So what are the following? So one, f is polynomial, which I'm not going to be quite as fancy and state that as the closure under the identity plus sums and products. I'm just going to, I mean, we could define it more intrinsically, but I'm just going to say that it's represented by one of these bridge diagrams. Okay, second condition, which is going to be much easier to check in practice. F is accessible. So that means that it preserves kappa filtered colimits for some cardinal kappa, which is sufficiently large. And preserves weakly contractible limits. What does that mean? Those are limits over, infinity categories whose geometric realization happens to be contractible. But you can also, it's equivalently, I mean, that makes it harder to check. Equivalently, what's called conical limits, where a diagram, that's where you take, you would normally have it, say, a D-shaped diagram in C, but I want to, I mean, the limit is conical if the indexing set has a terminal object, if the indexing category has a terminal object. So it can be written as limit indexed by a category that looks like this, the cone on some other category. So you don't have to check all weakly contractible limits, although evidently D cone is weakly contractible. And then the third is that F is a local right adjoint, which has been discussed, but it doesn't mean that F itself is a right adjoint, but for each X, well, if I map it to the slice over F of X, then that thing is a right adjoint. Okay, and so this is a slight improvement over Joyal's original exactness characterization of the polynomial functors because, well, we're working higher categorically, and that just makes things a little bit cleaner. Now, let's put back in the analyticity condition. So the next theorem that I want to advertise in the, say, 5 minutes that I have left is the following are equivalent again for a functor f from S over I to S over J. So one, f is polynomial and admits a map to exp. I didn't say what a map of polynomial functors is, but there's a built-in Cartesianness condition. Okay, 2, f is represented by a bridge. I take I take J here. I take my E and I take my B. I call this F, where F is an étale map. So it has finite discrete fibers. And the third condition is that F preserves sifted colimits and weakly contractible limits, or conical is still enough. Okay, so that's an abstract characterization of what analytic endofunctors from S over I to S over J are. And a remark, which this goes back, I'm sure, pretty far, but I can reference Joachim's 2011 paper on this. He can probably provide the initial reference, or maybe this is the initial reference. I'm not actually sure, but a tree gives rise to an analytic endofunctor. I'm just making a more explicit connection. So what you do is you take the marked nodes, which are nodes with a marked incoming edge. I'm just going to tell you the bridge diagram that it corresponds to. Then you just take the nodes of the tree. Since it's a tree, you know what the outgoing edge is, because trees always have a single edge under any node, but it can have a lot of edges over any node. And this is the incoming marked edge. So there's a way of encoding trees as analytic endofunctors. And this allows us, so I'm just going to wrap this up in the next couple minutes, but this allows us now we can reconstruct using this, the Mordaic Weiss dendroidal indexing category. Because we take trees, we view that as some subcategory of analytic endofunctors. And I didn't say this, but this is another theorem that we prove in this paper based on a whole history of the similar theorems in category theory. But something involving initial algebras, or to say it differently, we can form the free monad or say the free analytic monad. Oh, I'm using this for monad on an analytic endofunctor. And from that, the image of that is the Mordaic Weiss category omega. So now I can state the main theorem of the paper, which is that the restricted Yoneda embedding, so from analytic monads to presheaves on omega, this is the functor category omega up to S, is fully faithful with essential image those dendroidal, well, I'll say it this way, the dendroidal complete Siegel spaces. We usually write that P sub Siegel of omega. And this is by work corollary using work of Hoytz, Hinich, and Mordaic. This P Siegel over omega is known to be equivalent to the category of infinity operads as defined by Lurie. So that's a sketch of how our arguments go to compare analytic monads to the infinity category of infinity operads. And it goes through this theory of polynomial functors that we develop in the infinity context. And well, it's really a beautiful story because it is cleaner than the classical one in many respects. And I think would generalize to other contexts. And since many people have remarked on what the possible generalizations of this could be, I'd be very interested to hear people's thoughts on that. Okay, that's it. Thank you for listening.
Thanks, David. So, questions or comments? David.
Yeah. Hey, David, thanks for the talk. That's great. This is kind of probably coming out of nowhere, but if we don't have it's coming out of the Amin Ustali result that I think is so cool. Do you think there's any chance that if we don't look at just Cartesian maps, but all maps between polynomial functors in this way, and we look at comonoids in that, so in the set theoretic case, we get categories. Do you think we get category objects in spaces? Is it possible that we might repeat this, get complete Siegel spaces or something?
That's a great question. I would like to know the answer to that. I don't know if you'll get the completeness condition. One of the issues that comes up in the one categorical case is, do you get the one category of categories, or do you get the two categories?
Oh, you don't, right. You don't get the one category of categories. You get categories as objects, but you get strange morphisms.
Right. So
yeah. Okay, right. So that's the first weird thing.
Yeah, that's the first weird thing. But I would be it would be interesting to know what these strange morphisms are.
Right.
So that would be something to figure out.
Yeah. Okay, cool. Yeah, I mean, I knew you probably didn't know the answer, but I thought I'd just ask the question because it had to be asked somewhere. Thanks again.
Other questions? I have a comment. I think the theorem you attributed to Leinster is not true in the category of sets. You need to say weakly Cartesian or something.
Yeah, I mean, exactly. So here let's say the inspiration was certainly from Leinster's work, and there is a notion of weak Cartesian that makes that rigorous. Still, I mean, I certainly, as far as I know, the idea came from Leinster, so I thought it was appropriate to attribute it. But Joachim's right that if you just work in the category of sets, you don't really get an actual Cartesian morphism. But you do the moment you work in what Clausen and Schulze would call animated sets.
And maybe if you do the weakly Cartesian case, maybe it's rather due to Joyal than to Leinster. I don't know.
Well, there's so much of this is due to Joyal. It's yeah, I would probably agree with that statement, but if André is listening, he might be able to clarify.
Any other questions? Comments? Then maybe we should just thank David again and say it's enough for today. Thanks. And in case anybody is interested, Nicola actually found this map of the prehistory of polynomial functors that from 2010. So if you want, here it is. I don't know, can you see it? So this was drawn in 2010. So it's of course not at all up to date. And maybe it was never up to date, who knows? But it's mostly Peter Johnson who told me all these things. So now that Nicola has found it, maybe it could go on the website. Maybe I'll write to Peter Johnston. Okay. Anything else before we finish? So I think the slides will very soon, or maybe they are already, be on the webpage. And I think the videos are still available on YouTube. Is that true?
Yes, they should be on YouTube. Yep, they're on YouTube, and hopefully the website, topos.site thing that's in the chat, we'll have all the YouTube videos linked there too.
Okay, then maybe we should just stop for today and see you all tomorrow.
Okay, bye all.
Bye, and